Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into Earth's molten birth, back when stone itself was still just a dream floating in the darkness of space. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined a long thank you. 4.5 billion years ago, there is no Earth yet. There is no sun blazing at the centre of our solar system. No familiar planets tracing their well-worn elliptical paths through the void. No moon to pull tides across oceans that do not exist. There is only the solar nebula, a vast, rotating disk of dust and gas that stretches beyond the furthest reaches of human imagination, spinning with the leisurely, hypnotic grace of deep time itself in the cold vacuum where our entire solar system will eventually find its home. This nebular disk extends outward for billions of kilometers, a gossamer-thin collection of matter so diffuse that most of it qualifies as empty space, yet containing within its gentle spiral arms all the raw materials that will someday compose planets and moons and asteroid belts and the countless smaller bodies that populate interplanetary space. The temperature here hovers perpetually near absolute zero, that theoretical point where atomic motion nearly ceases entirely and molecules slow their eternal dance to something approaching stillness. In this profound cold, particles of silicon drift alongside specks of iron. Fragments of magnesium mingle with dust grains of aluminum, calcium, nickel, and countless other elements that will someday compose mountain ranges and ocean floors, and the iron cores of worlds. Each individual grain measures smaller than anything the human eye could ever perceive, smaller than bacteria, smaller than the wavelength of visible light itself, yet each carries within its atomic structure the potential for continents. They move through this cosmic medium with the infinite patience that only geological time can teach, following orbital paths so vast and so gradually curved that their motion appears almost linear, like snow falling through air so still it might as well be solid. Occasionally, after drifting for centuries without contact, two particles bump into one another with touches so gentle they barely register as physical interaction. The collision happens at velocities measured in mere centimeters per second, slower than the growth of fingernails, gentler than the settling of dust on a windowsill. Sometimes, through forces so weak they hardly qualify as bonds, these microscopic fragments somehow manage to stick together. The process unfolds with a slowness that makes glaciers seem hurried, makes erosion appear violent, makes the growth of mountains look like sudden eruptions. Each successful connection between particles represents not moments or hours or even years, but thousands upon thousands of years of cosmic choreography, of orbital mechanics playing out across scales that dwarf human comprehension. Individual dust grains take millennia to find their partners in this vast, cold dance, and when they finally do encounter one another through the patient working of gravity and chance, they form clusters no larger than the pebbles a child might collect along a beach, though these pebbles exist without beaches, without oceans, without ground of any kind, suspended in the weightless drift of interplanetary space, turning end over end in orbits governed by laws written in the most fundamental language the universe knows, the mathematics of gravity and momentum and angular momentum conservation, Scientists have given this process the technical name accretion, though the word carries connotations of urgency and accumulation that feel almost violently inappropriate for something that unfolds with such extraordinary, almost meditative leisure. These cosmic pebbles, having invested thousands of years in their own formation, now spend tens of thousands more in the patient work of gathering their neighbours into collections the size of rocks. The rocks, in turn, dedicate millions of years to the gradual accumulation of partners, slowly building into boulders that tumble through space like ancient, silent sculptures. The boulders eventually grow into objects approaching the size of mountains, though mountains that exist without any context except the endless black of space and the distant, cold light of stars still condensing from their own nebular material in regions of the galaxy far from this particular stellar nursery. The scientific mystery that lingers here, patient as the accretion process itself, involves the precise mechanism by which these infinitesimal particles manage to overcome their natural tendency to bounce apart when they collide. The physics of the situation suggest that impacts between dust grains should result in fragmentation rather than aggregation, yet somehow aggregation wins out often enough to build worlds. Current theoretical models propose that static electricity might play a crucial role. The same electrostatic force that makes hair stand up after rubbing a balloon or causes socks to cling together in a dryer. Though operating here on scales both vastly larger and impossibly smaller than human daily experience. Perhaps the van der Waals force contributes significantly that whisper-weak attraction between molecules that becomes noticeable only when surfaces approach each other very closely, somehow managing to hold cosmic dust together just long enough for gravity to gradually take over the work of assembly. But no human being has ever directly observed this fundamental process happening. No laboratory on Earth can perfectly replicate the precise environmental conditions of the primordial solar nebula, with its specific temperature gradients and pressure variations and electromagnetic field configurations and radiation levels, and the countless other variables that influence how matter behaves in such extreme conditions. So this most essential step in planetary formation, the critical moment when scattered matter first decides to abandon its individual existence and begin the collaborative work of becoming a world, remains beautifully, mysteriously, quietly uncertain, like a fundamental question written in a language we can almost but not quite translate. The ironies embedded in this process settle here in layers, like sediment accumulating on an ocean floor that will not exist for hundreds of millions of years yet. The sequence of events that will eventually create the most geologically dynamic, tectonically active, volcanically restless planet in the known solar system begins in conditions of nearly perfect stillness, where movement happens so slowly that entire mountain ranges could rise and fall on modern Earth in the time it takes a single dust grain to drift from one side of the forming solar system to the other. The forces that will someday drive continental plates across Earth's surface with enough accumulated power to raise the Himalayas and split the Atlantic Ocean and reshape the entire geography of continents start here as interactions so delicate, so gentle, that they could be disrupted by disturbances too small to measure with any instrument humans have yet devised. The world that will eventually teem with billions of different species of life, from the smallest bacteria to blue whales, from redwood trees to microscopic plankton, begins its existence as completely sterile dust suspended in a void so profoundly empty that individual particles can drift for centuries, sometimes for millennia, without encountering so much as a single neighbour. The planet that will develop weather systems and ocean currents and atmospheric dynamics complex enough to sustain life, begins as matter so cold and still that it makes the vacuum of space seem bustling with activity. Here, in this pre-planetary quiet that stretches across geological epochs, time moves like honey cooling a winter that promises never to end. 1,000,000 years passes a temporal span that encompasses the entirety of recorded human history dozens of times over. That includes the rise and fall of civilizations, the evolution of species, the formation and erosion of landscapes, and the largest objects in what will someday become Earth's immediate cosmic neighborhood are perhaps the size of the asteroids that occasionally streak across our modern sky. Irregular chunks of rock and metal tumbling through space in eccentric, unpredictable orbits that very occasionally, through the patient working of celestial mechanics, cross paths with their neighbours when these protoplanetary fragments do finally meet after eons of separate wandering. The collisions happen at velocities that would instantly vaporize any rock existing on today's Earth, speeds measured in kilometers per second that would turn granite into plasma and iron into expanding clouds of gas. Yet somehow, impossibly, through mechanisms that planetary scientists continue to debate in academic conferences and research papers, these violent encounters sometimes result not in mutual destruction, but in gentle merger, as if the universe has not yet learned the devastating art of catastrophic impact, as if matter itself is still practicing the fundamental skills of becoming solid and remaining that way despite the forces trying to tear it apart. The ambient temperature of the space surrounding this slow-motion construction project holds steady at approximately minus 270 degrees Celsius, a cold so profound and absolute that it approaches the theoretical limits of coldness itself, that point where atomic motion slows to almost nothing, and the fundamental particles that comprise all matter hover on the edge of complete stillness. At such temperatures, nearly every substance that humans have ever encountered in their brief terrestrial experience would exist only as frozen crystals, brittle and lifeless as ancient ice preserved in polar glaciers that have never known the touch of sunlight. Carbon dioxide, which flows invisibly through Earth's modern atmosphere and sustains the photosynthetic processes that feed all plant life, becomes solid snow that would shatter like the most delicate glass at the slightest touch. Water, that most essential medium of all life as we know it, the substance that comprises the majority of every living cell, transforms into a material harder than the steel used to construct the tallest skyscrapers and longest bridges. Even helium, that most reluctant of elements to condense under any circumstances, that noble gas which resists chemical bonding with the stubborn independence that characterizes its entire family in the periodic table, begins to consider the remote possibility of becoming liquid under such extreme conditions, though it maintains its resistance with the determined aloofness that has made it useful for filling balloons precisely because of its refusal to react with anything. Hydrogen, the most abundant element in the universe and the primary constituent of the stellar material slowly condensing into what will become our sun, exists here as a solid so hard it could serve as construction material. If there were anyone present to construct anything, if there were any purpose for construction in this realm where matter follows only the patient laws of physics, yet within this cosmic deep freeze, buried in this realm of absolute cold that makes the most severe Antarctic winter seem tropical by comparison, the seeds of what will become the most molten, volcanic, geologically restless world in the solar system are slowly, methodically, grain by grain, taking their first tentative shape. The irony writes itself across the void in letters too large to read, except from the perspective of deep time. In a script composed of orbital mechanics and gravitational interactions that will not be decoded by conscious minds for billions of years, the planet that will someday feature surface temperatures hot enough to melt lead and vaporize zinc begins its formation in conditions cold enough to freeze the very atmosphere that terrestrial life will someday breathe. As millions of years accumulate like dust settling on a cosmic windowsill that spans the breadth of the inner solar system, the largest aggregations of matter in this region of space grow steadily from pebble size to boulder size to mountain size. Though these familiar designations carry little meaning in an environment without gravity strong enough to define concepts like up and down, without atmosphere to provide the resistance and friction that make motion feel substantial, without any of the familiar reference points that allow human perception to make sense of scale and distance and relative size. These protoplanetary bodies tumble through the vacuum in complex, overlapping orbits that follow the mathematical laws of celestial mechanics with the perfect precision that characterizes all natural phenomena, yet appear random and chaotic to any hypothetical observer attempting to predict where any particular object will be located at any given moment in the far future. The scientific mystery deepens and becomes more intriguing as these objects grow larger and their gravitational influence begins to extend farther into the surrounding space, creating zones of influence that reach well beyond their physical boundaries. Current theoretical models suggest that once a protoplanetary body reaches approximately 1 kilometer in diameter, roughly the size of a large asteroid in today's solar system, its gravitational field becomes strong enough to significantly influence the motion of nearby dust particles and smaller objects, creating what planetary scientists call gravitational focusing. The remarkable ability to collect material from a much larger area of space than the object's physical cross-section would normally allow through simple geometric collision probability. This represents a crucial threshold in planetary formation, a tipping point where the character of growth transitions from the painfully slow process of direct collision, which depends entirely on the chance encounter of objects following intersecting orbital paths, to the more efficient mechanism of gravitational accumulation, where the growing protoplanet begins to actively influence its environment and gather material from an ever-widening sphere of influence. Yet the precise details of this transition, the exact mechanisms by which gravitational focusing operates under the specific conditions of the early solar system, remain frustratingly unclear to modern planetary science. Hidden in the complex mathematical interplay between gravity, orbital mechanics, collision dynamics, and the physical properties of primitive solar system materials that no laboratory on Earth can perfectly replicate. The process that emerges from these conditions resembles nothing so much as a cosmic game of gravitational billiards played in extreme slow motion across millions of years, with rules that become more complex as the players grow larger and their gravitational influence extends farther into space. Objects that began their existence as individual dust grains smaller than bacteria, then became pebbles no larger than marbles, then rocks the size of boulders, now exist as irregular chunks of loosely consolidated material ranging from structures comparable to city blocks to formations approaching the size of small mountains, though mountains that exist without peaks or valleys, without weather to erode them, without any of the familiar geological processes that shape terrestrial landscapes. They follow elliptical orbits around the gravitational center, where the sun is slowly condensing from its own vast collection of nebular material, occasionally intersecting with the orbital paths of their neighbors in encounters that occur perhaps once every few thousand years, meetings that have been mathematically inevitable since the moment their orbits were established by the initial conditions of the solar nebula's collapse. When these cosmic appointments finally arrive, they represent collisions between objects that have been building toward this singular moment for geological ages, encounters freighted with the accumulated potential energy of eons. The proto-Earth grows through these encounters like a snowball rolling downhill. If the hill were the size of the solar system and the rolling took millions of years, each successful merger adding not just mass but angular momentum, kinetic energy converted to heat, an increasingly complex internal structure that reflects the varied composition of the impacting bodies. The early collisions between relatively small objects moving at modest velocities might result in gentle accretion, with the smaller body simply adhering to the larger one like a cosmic snowball gathering more snow, the impact energy insufficient to cause significant heating or structural disruption. But as the objects grow larger and their mutual gravitational attraction increases, and as gravitational focusing causes more distant objects to be drawn into collision courses, the relative velocities at impact begin to increase dramatically. These encounters release energy measured in the same units used to describe nuclear explosions, though the energy dissipates over much longer timescales and much larger volumes of space. The accumulated heat from these increasingly violent collisions begins to warm the growing protoplanet, marking a fundamental transition in its character from a cold aggregation of cosmic debris to something approaching a warm, perhaps even hot, celestial body whose internal temperature reflects the violence of its formation. The iron and nickel within the consolidated material, originally frozen solid as interstellar ice in the cold depths of the solar nebula, begins to soften under the accumulated thermal energy of countless impacts, each collision adding to a heat budget that grows larger with every passing millennium. Lighter materials, particularly those containing significant amounts of water ice and frozen carbon dioxide that were incorporated during the early stages of accretion, start to sublime directly from solid to vapor without passing through the intermediate liquid phase, creating the first thin wisps of what might generously be called an atmosphere, though one so tenuous and ephemeral that it barely qualifies as gas rather than a slightly elevated vacuum decorated with occasional molecules. This primitive atmosphere bears no resemblance to the oxygen-rich envelope that will someday sustain complex life, nor even to the carbon dioxide-dominated atmospheres that characterize Venus and early Mars. Instead, it consists primarily of water vapor and carbon dioxide escaping from the warming surface materials, along with traces of methane, ammonia, and other simple compounds that represent the chemical inventory of the original nebula materials. The atmospheric pressure measures so low that any liquid water, should any manage to form, would immediately boil away into space, regardless of temperature, a physical impossibility that will persist until the growing planet accumulates enough mass to generate gravitational fields strong enough to retain a substantial gaseous envelope. The mathematical beauty of orbital mechanics ensures that not all collisions between protoplanetary objects result in successful accretion and growth. Some encounters occur at velocities too high for the gravitational binding energy of the objects to overcome their kinetic energy of approach, resulting instead in catastrophic fragmentation that sends debris flying in all directions across the solar system. These hit-and-run collisions follow the same physical laws that govern successful mergers, yet produce dramatically different outcomes depending on subtle variations in approach angle, impact velocity, and the internal structure of the colliding bodies. The fragments created by these destructive encounters follow complex trajectories determined by the vector sum of their original orbital motion and the impulse imparted by the collision. Some pieces travel at velocities that carry them beyond the gravitational influence of the proto-Earth entirely, destined to wander the outer reaches of the solar system for eons, or perhaps to be captured eventually by the growing gas giants that are simultaneously condensing in the more distant regions of the nebular disk. Other fragments receive just enough energy to enter highly elliptical orbits that will eventually bring them back into the vicinity of the proto-Earth, though perhaps not for thousands or tens of thousands of years, creating a complex population of debris that continues to interact with the growing planet across extended timescales. These hit-and-run collisions contribute their own layer of subtle irony to the planetary formation process in order to successfully build a stable, coherent planet capable of retaining a permanent atmosphere and eventually supporting life. The proto-Earth must survive countless encounters that possess the potential to destroy it entirely, to fragment it back into constituent pieces and scatter those pieces across interplanetary space. The difference between construction and destruction often depends on factors so small they approach the limits of measurement. Slight variations in impact angle measured in degrees, differences in approach velocity measured in meters per second, variations in the internal density and structural integrity of the colliding objects that depend on the precise sequence of their own formation histories. The growing proto-Earth develops an increasingly complex internal structure as the accumulating mass creates gravitational fields strong enough to overcome the structural strength of rock and metal, heavier materials, particularly iron and nickel that will eventually form the planet's core, begin to sink toward the center under the relentless pull of gravity, while lighter silicate materials rich in aluminum, silicon, and oxygen float toward the surface like oil separating from water. Though the process occurs in solid and semi-solid materials rather than fluids, and takes millions of years to approach anything resembling completion, this process, which planetary scientists call differentiation, proceeds with the same geological patience that characterizes all aspects of planetary formation, establishing the basic core mantle crust structure that will eventually define Earth's internal architecture and drive the tectonic processes that reshape its surface. The energy released by this gravitational settling, as dense materials sink through lighter ones and potential energy converts to heat, adds significantly to the thermal budget of the forming planet, contributing to an internal environment that grows steadily warmer with each passing geological epoch. The heat generated by differentiation combines with the thermal energy from ongoing impacts to create temperature gradients within the proto-Earth that would be lethal to any conceivable form of life, though life remains an impossibility for numerous other reasons related to the absence of stable surface conditions, liquid water, and the complex chemistry that will eventually emerge from more stable environmental conditions. The interior temperatures begin to approach the melting points of common rock-forming minerals, creating zones of partial melting where solid crystals coexist with pockets of liquid magma, establishing the conditions that will eventually lead to volcanic activity and the complex geochemical processes that will reshape the planet's surface composition. Throughout this extended period of violent construction that spans tens of millions of years, the proto-Earth maintains no stable surface, no consistent atmospheric composition, no recognizable geography that would persist long enough to be mapped or studied. Its appearance changes constantly as new impacts add material and rearrange the distribution of mass, as differentiation drives internal reorganization, as the heat generated by these processes creates localized zones of melting and chemical alteration. The boundary between solid surface and space remains fluid and constantly redefined by the latest collision or the most recent episode of internal reorganization. Any hypothetical observer positioned at a safe distance from this dynamic construction site would see not a planet in any familiar sense, but rather a constantly changing aggregate of cosmic debris held together by its own gravity and shaped by the relentless accumulation of kinetic energy from countless impacts. The surface glows with the dull red heat of repeated collisions, punctuated by the brilliant flashes of new impacts that temporarily illuminate the surrounding space with light bright enough to be visible across interplanetary distances. The proto-Earth resembles less a solid world than a gravitational gathering point for cosmic debris, a three-dimensional intersection of orbital mechanics where matter accumulates according to the patient mathematics of celestial mechanics. The timescales involved in these formative processes stretch beyond easy human comprehension, requiring a fundamental shift in temporal perspective to appreciate their true character. Individual collisions might be separated by thousands or tens of thousands of years, intervals long enough for entire civilizations to rise and fall, for species to evolve and go extinct, for continents to shift position on a modern Earth. Yet from the perspective of planetary formation, these events occur in rapid succession, like raindrops falling during a summer storm, each impact building on the accumulated effects of all previous encounters to drive the proto-Earth toward the critical mass and internal temperature necessary for the next phase of its development. The proto-Earth's mass doubles, then doubles again, then continues growing in a progression that appears exponential when viewed across millions of years, but feels glacially slow when measured against the lifetime of any individual object involved in the accretion process. This mathematical progression follows the laws of gravitational dynamics, where larger objects capture material from increasingly large volumes of space, accelerating their own growth in a positive feedback loop that will eventually dominate the local environment and sweep up most of the available solid material within the orbit that will someday be called Earth's zone in the solar system. The growing proto-Earth begins to exert its gravitational influence across an ever-widening sphere of space, fundamentally altering the orbital dynamics of the entire inner solar system through what amounts to cosmic-scale environmental engineering that operates according to the patient mathematics of celestial mechanics. Objects that once followed stable, predictable elliptical orbits around the condensing sun now find their trajectories gradually perturbed by the increasing mass concentration that will eventually become our planet. These gravitational perturbations accumulate over thousands of orbital periods, causing small asteroids and larger protoplanetary fragments to spiral slowly inward toward collision courses that were not predetermined by the original conditions of the solar nebula, but emerge from the complex interplay between growing planetary masses and the fundamental laws of orbital mechanics. The scientific mystery embedded in this phase of planetary formation involves the precise mechanisms by which a growing planet manages to avoid disrupting its own accretion process through gravitational interference. Theoretical models suggest that as the proto-Earth approaches approximately 10% of its final mass, roughly equivalent to the mass of modern Mars, its gravitational field becomes strong enough to significantly alter the orbital characteristics of nearby objects, potentially scattering away the very material it needs to continue growing. This represents a delicate balance between gravitational capture and gravitational disruption, a cosmic tightrope walk where success depends on maintaining growth rates that fall within narrow mathematical boundaries defined by orbital resonances and the competing gravitational influences of other growing planets. Current understanding of this process remains frustratingly incomplete, limited by the impossibility of directly observing planetary formation in action and the extraordinary computational complexity required to model the simultaneous gravitational interactions of millions of individual objects across timescales spanning millions of years. The most sophisticated computer simulations can follow the evolution of perhaps a few thousand representative particles for a few million simulated years, a sample size and duration that captures only the broadest outlines of processes that actually involve countless billions of objects interacting across tens of millions of years of real time. The heat budget of the proto-Earth continues to grow with each collision, creating internal temperatures that begin to approach and occasionally exceed the melting points of common rock-forming minerals such as olivine, pyroxene, and feldspar. This thermal evolution marks another crucial threshold in planetary development, the point where the growing world transitions from an essentially solid aggregate of cosmic debris to a partially molten body capable of supporting the complex internal dynamics that will eventually drive plate tectonics, volcanism, and the geochemical processes that will create and maintain the conditions necessary for life. The first pockets of liquid rock begin to form deep within the proto-Earth's interior, where the combination of impact heating, gravitational compression, and the heat released by ongoing differentiation creates temperatures exceeding 200 degrees Celsius. These initial magma chambers exist as small, isolated pools of molten material surrounded by solid rock that still retains the primitive composition and structure inherited from the original nebular condensation process. The liquid rock possesses a lower density than the surrounding solid material, creating buoyancy forces that drive it slowly upward toward the surface through cracks and fractures in the overlying solid layers. The irony of this thermal evolution lies in its reversal of the normal relationship between temperature and depth that will characterize the mature Earth. In today's world, temperatures generally increase with depth according to the geothermal gradient, reaching their maximum values at the core mantle boundary, some 2,900 kilometers below the surface. But during the Hadean formation period, the highest temperatures often occur near the surface, where the most recent impacts have deposited their kinetic energy, while the deep interior remains relatively cool, composed of materials that have not yet experienced sufficient compression and heating to reach their melting points. This temperature inversion creates convection patterns unlike anything that will exist during later periods of Earth's history. Hot surface materials, heated to glowing temperatures by impact energy, gradually sink into the cooler interior, while cooler deep materials rise toward the increasingly hot surface in a complex three-dimensional circulation pattern that operates across timescales measured in millions of years. These convection currents drive the first large-scale mixing processes within the proto-Earth, beginning the homogenization of chemical composition that will eventually create the differentiated structure of core, mantle, and crust that defines the modern planet's internal architecture. The surface of the proto-Earth during this period bears no resemblance to any landscape that will ever exist on the mature planet. Instead of solid ground covered by soil and vegetation, or even bare rock sculpted by erosion and tectonic forces, the surface consists of a constantly changing mosaic of impact craters in various stages of formation and modification, separated by regions of cooling lava flows and zones of upwelling molten material. The temperature varies dramatically both spatially and temporally, ranging from the searing heat of fresh impact sites, where surface temperatures can exceed 2,000 degrees Celsius, to relatively cool areas that have had time to radiate their energy into space and approach the freezing point of water. The atmospheric composition during this period reflects the ongoing violence of planetary construction. Each major impact vaporizes significant quantities of surface rock, adding silicate vapor to the thin gaseous envelope surrounding the proto-Earth. This creates an atmosphere composed primarily of rock vapor, a concept so alien to modern experience that it requires considerable imagination to visualize. Silicon dioxide, aluminum oxide, and magnesium oxide, substances that exist as solid crystals under normal terrestrial conditions, float as invisible gases in the tenuous atmosphere of the forming planet, creating conditions that will not be duplicated anywhere in the solar system once planetary formation concludes. The pressure of this rock vapor atmosphere remains extremely low by terrestrial standards, perhaps 1,000th the pressure of modern sea-level air, yet it represents a significant increase over the near-vacuum conditions that characterize the earlier stages of accretion. This atmospheric thickening creates the first primitive greenhouse effect in Earth's history, as the rock vapor absorbs and re-radiates thermal infrared radiation more efficiently than the previous near-vacuum conditions. Beginning the complex feedback processes between surface temperature, atmospheric composition, and planetary energy balance that will eventually regulate Earth's climate, the magnetic field of the proto-Earth, if it exists at all during this period, remains weak and intermittent, generated by the chaotic convection of partially molten metallic material in the forming core rather than the organized circulation patterns that will eventually create the stable dipolar field that protects modern Earth from solar radiation. This magnetic weakness leaves the thin atmosphere vulnerable to erosion by the solar wind, the stream of charged particles flowing outward from the young sun, which strips away atmospheric gases at rates much higher than will be tolerated once a stronger magnetic field develops. The day length during this period fluctuates wildly as large impacts transfer angular momentum to or remove it from the rotating proto-Earth. Some collisions, particularly those that strike the planet at oblique angles, can significantly speed up or slow down the rotation rate, causing the length of the day to vary by hours or even days from one impact to the next. This rotational instability contributes to atmospheric and surface dynamics unlike anything that will characterize later periods of Earth's history, creating weather patterns and circulation systems that operate under constantly changing boundary conditions. The growing planet sweeps up material from an increasingly large volume of space as its gravitational cross-section expands, accelerating the accretion process in a positive feedback loop that will eventually lead to runaway growth once a critical mass threshold is reached. This gravitational focusing effect means that the rate of mass accumulation increases exponentially rather than linearly, transforming the proto-Earth from a minor player in the solar system's gravitational dynamics to an increasingly dominant force that will eventually capture or scatter most of the solid material within its orbital zone. The mathematical inevitability of runaway accretion begins to assert itself as the proto-Earth approaches approximately 1/4 of its final mass, crossing a threshold where gravitational focusing becomes so efficient that the planet begins to dominate the orbital dynamics of everything within its expanding sphere of influence. Objects that previously followed stable trajectories around the young sun now find themselves drawn inexorably toward collision courses with the growing world, their orbital energy slowly bleeding away through gravitational interactions that operate like cosmic friction, invisible but inexorable. This represents the beginning of the end for the chaotic, debris-filled environment that has characterized the inner solar system since the collapse of the original solar nebula, as the proto-Earth transforms from merely another large object among many into the gravitational overlord of its orbital neighborhood. The process unfolds with the same patient persistence that marks all aspects of planetary formation. Yet the consequences accelerate dramatically as the growing planet's gravitational reach extends farther into space. What began as occasional random collisions between objects following independent orbits evolves into systematic gravitational harvesting, where the proto-Earth actively captures material from volumes of space hundreds of times larger than its physical cross-section. The mathematical beauty of this transition lies in its self-reinforcing character. Each successful capture adds mass that increases gravitational attraction, which enables more efficient capture of additional material, which adds more mass, creating an exponential growth curve that will transform the inner solar system from a realm of countless independent objects into a much simpler arrangement of widely separated planets. The heat generated by this accelerating bombardment begins to fundamentally alter the physical state of the proto-Earth's interior, creating conditions that have no analogue in the modern solar system and will never be duplicated once planetary formation concludes. The accumulated thermal energy from millions of impacts drives internal temperatures well above the melting points of most common rock-forming minerals, creating vast zones of partially molten material that extend from the surface down to depths of several hundred kilometers. This represents the birth of what planetary scientists call a magma ocean, though the term ocean implies a stability and permanence that this violent, constantly churning environment completely lacks. The magma ocean exists in a state of continuous turbulent convection, driven by the constant input of impact energy from the surface and the ongoing release of gravitational potential energy as denser materials sink toward the center and lighter materials rise toward the surface. The circulation patterns within this molten realm operate on timescales ranging from days for near-surface flows to millions of years for deep convection cells that extend through the entire thickness of the partially molten zone. These convection currents create the first large-scale chemical mixing processes in Earth's history, beginning the homogenization and differentiation that will eventually separate the planet's interior into the distinct chemical and physical layers that characterize its modern structure. The scientific mystery that haunts this period involves the precise mechanisms by which heat escapes from the proto-Earth's interior to prevent complete melting of the entire planetary mass. Theoretical calculations suggest that if all the kinetic energy from major impacts were retained within the planet, the internal temperatures would rise high enough to completely vaporize even the most refractory materials, transforming the entire proto-Earth into an expanding cloud of rock vapor that would dissipate into space rather than condensing into a solid world. Yet somehow, through processes that remain poorly understood, the growing planet manages to radiate away enough thermal energy to maintain at least some solid structure. Even as impact rates reach their maximum intensity, current models propose that the key lies in the efficiency of thermal radiation from the glowing surface, which operates according to the Stefan Boltzmann law and increases proportionally to the fourth power of absolute temperature. As impact heating drives surface temperatures higher, the rate of energy lost to space increases dramatically, eventually reaching equilibrium with the rate of energy input from ongoing bombardment. This thermal balance represents another delicate tightrope walk in planetary formation, where success depends on maintaining impact rates high enough to drive continued accretion, but not so high that they completely overwhelm the planet's ability to dissipate the resulting heat. The surface temperature during the peak of this bombardment period reaches levels that would vaporize most materials instantly, creating a perpetual shroud of rock vapor that obscures the solid surface beneath like a planetary-scale industrial accident. Silicon dioxide, magnesium oxide, iron oxide, and aluminum oxide float as gases in an atmosphere that bears no resemblance to any modern planetary environment. creating optical properties that would make the proto-Earth appear as a glowing red-orange beacon visible across interplanetary distances. The atmospheric pressure, while still low by terrestrial standards, increases dramatically as impact vaporization adds material faster than thermal escape can remove it, creating the first substantial gaseous envelope in Earth's history. This rock vapor atmosphere possesses greenhouse properties far more extreme than anything caused by carbon dioxide or water vapor in modern terrestrial climates. The complex molecular structure of silicate gases creates absorption bands throughout the infrared spectrum, trapping thermal radiation with an efficiency that drives surface temperatures even higher than the already extreme levels created by direct impact heating. This atmospheric greenhouse effect represents the first example of climate feedback in Earth's history, demonstrating how changes in atmospheric composition can amplify or moderate the effects of external energy sources. The magnetic field generated by the proto-Earth during this period remains chaotic and variable, reflecting the turbulent convection patterns in the partially molten metallic core that has begun to differentiate from the surrounding silicate materials. Unlike the stable dipolar field that will eventually protect Earth's atmosphere from solar wind erosion, this early magnetic field consists of multiple, rapidly changing poles that provide little protection against charged particle bombardment from space. The combination of weak magnetic shielding and extreme surface temperatures creates atmospheric loss rates thousands of times higher than anything that will characterize later periods of Earth's history. The rotational dynamics of the proto-Earth during this bombardment phase remain highly unstable, as large impacts continue to transfer angular momentum in random directions, causing the rotation rate and axis orientation to fluctuate wildly over timescales ranging from individual impacts to thousands of years. Some theoretical models suggest that particularly massive collisions during this period might have been capable of stopping the planet's rotation entirely, or even reversing its direction, creating episodes where the sun would rise in the west and set in the east. If anyone had been present to observe such phenomena, and if the surface conditions had permitted the existence of recognizable sunrise and sunset, the chemical composition of the magma ocean evolves continuously as ongoing impacts add material with varying elemental abundances, while fractional crystallization and gravitational settling remove different components at different rates. The earlier stages of differentiation begin during this period, as the densest materials, particularly metallic iron and nickel, sink toward the center to form the first recognizable core, while the lightest materials, particularly those rich in aluminum and silicon, float toward the surface to begin the process of crustal formation. This chemical separation occurs against the background of constant mixing caused by impact-driven convection, creating a dynamic equilibrium between differentiation and homogenization that will persist until impact rates finally decline enough to allow stable layering to develop. The timescales involved in this peak bombardment period compress the most violent aspects of planetary formation into a relatively brief interval, perhaps spanning only a few million years despite the geological context that surrounds it. During this compressed time frame, the proto-Earth experiences more large impacts than it will encounter during all the remaining billions of years of its existence, creating surface conditions so extreme that they serve as a baseline for comparison when planetary scientists discuss the most hostile environments anywhere in the solar system. The irony embedded in this violence is that these same extreme conditions drive the chemical and physical processes that will eventually create the stable, differentiated planet capable of supporting the complex geology and atmospheric dynamics that will make life possible. The proto-Earth's gravitational dominance over its orbital zone reaches a mathematical tipping point where the capture efficiency approaches unity. meaning that virtually every solid object within a vast spherical volume of space centered on the growing planet will eventually be drawn into a collision course through the inexorable working of orbital mechanics. This represents the transition from chaotic bombardment, where impacts occurred as random encounters between independent objects following intersecting trajectories, to systematic gravitational sweeping, where the proto-Earth actively reshapes the orbital environment to maximize its own growth rate. The mathematical elegance of this process lies in its self-organizing character. The more massive the planet becomes, the more efficiently it captures additional material, creating a runaway feedback loop that will transform the cluttered inner solar system into the relatively empty space that characterizes the modern Earth-Moon system. The largest impacts during this period involve collisions with objects comparable in size to modern asteroids. Protoplanetary fragments that have themselves been growing through accretion for millions of years before their orbital paths finally intersect with the proto-Earth's expanding gravitational influence. These encounters release energy equivalent to millions of nuclear explosions concentrated into areas measuring hundreds of kilometers across, creating impact craters that would dwarf any geological feature on the modern Earth's surface. The Chicxulub crater, which marked the end of the dinosaurs and represents one of the most catastrophic events in Earth's recorded geological history, would appear insignificant compared to the routine bombardment that characterizes this formative period. The energy released by these massive impacts drives surface temperatures to levels that challenge the fundamental stability of matter itself, creating conditions where the distinction between solid and liquid phases becomes meaningless across vast areas of the planetary surface. Impact sites glow with temperatures exceeding 3,000 degrees Celsius, hot enough to melt platinum and vaporize copper, transforming ordinary rock into expanding clouds of superheated gas that rise like nuclear mushroom clouds into the thin atmosphere. The shock waves generated by these collisions propagate through the solid portions of the proto-Earth at velocities approaching the speed of sound in rock, creating global seismic events that would register beyond the limits of any earthquake magnitude scale ever devised. The scientific mystery that emerges from this bombardment involves the paradoxical relationship between destruction and construction in planetary formation. Each major impact possesses sufficient energy to excavate craters dozens of kilometers deep and hundreds of kilometers across, removing vast quantities of material from the impact site and ejecting it at velocities that often exceed the proto-Earth's escape velocity. By purely mathematical calculation, the cumulative effects of this continuous excavation should prevent the planet from growing beyond a certain maximum size, as impact erosion removes material faster than gravitational capture can add it. Yet somehow the proto-Earth continues to grow despite this apparent contradiction, suggesting the operation of geological processes that remain poorly understood, even with modern theoretical models and computer simulations. Current hypotheses suggest that the key lies in the complex three-dimensional dynamics of impact ejecta, where material blasted away from impact sites follows ballistic trajectories that often bring it back into collision with the planet at locations far from the original impact. This creates a global redistribution system where material removed from one region of the surface is deposited in other regions, maintaining the total planetary mass even as individual impacts appear to cause net loss. The mathematics of this process depend on subtle relationships between impact velocity, escape velocity, atmospheric drag, and gravitational focusing that combine to create retention efficiencies much higher than simple geometric calculations would predict. The atmospheric composition during this peak bombardment period evolves into something unprecedented in the modern solar system, a gaseous mixture dominated by rock vapor, maintained at temperatures and pressures that exist nowhere else in nature. Silicon dioxide, the primary constituent of most terrestrial rocks, exists as an invisible gas mixed with vaporized metals, oxides, and trace amounts of the volatile compounds that will eventually condense to form Earth's oceans and atmosphere. This rock vapor atmosphere possesses optical and thermal properties that create a greenhouse effect orders of magnitude more intense than anything caused by carbon dioxide or methane in modern planetary atmospheres. The density structure of this exotic atmosphere varies dramatically with altitude, creating layers and boundaries unlike anything that characterizes normal planetary atmospheres composed of relatively simple molecular gases. Near the surface, where temperatures remain highest, the atmosphere consists of a dense mixture of vaporized silicates that behaves more like a liquid than a gas, with convection currents that transport heat and material upward at velocities measured in meters per second. At higher altitudes, where temperatures drop below the condensation points of various minerals, the atmosphere transitions through a series of distinct layers where different compounds rain out of the vapor phase, creating precipitation patterns that consist of microscopic crystals of olivine, pyroxene, and feldspar rather than water droplets. The magnetic field generated by the proto-Earth during this period reflects the chaotic state of the partially molten core, where convection patterns change rapidly in response to the continuous input of thermal energy from surface impacts and the ongoing gravitational settling of dense metallic materials. Unlike the stable, dipolar magnetic field that will eventually protect Earth's atmosphere and enable the existence of complex life, this early magnetic field consists of multiple, rapidly shifting poles that provide minimal protection against the erosion effects of solar wind and cosmic radiation. The field strength varies by orders of magnitude over timescales ranging from days to thousands of years, creating episodes of strong magnetic shielding, alternating with periods of complete vulnerability to charged particle bombardment from space. The rotational dynamics of the proto-Earth during this bombardment phase remain dominated by the chaotic transfer of angular momentum from large impacts, creating a planetary rotation that bears no resemblance to the stable 24-hour day cycle that will eventually characterize the mature Earth. Individual impacts can change the length of the day by hours or even days, while particularly massive collisions at oblique angles can alter the orientation of the rotation axis by degrees, creating precession and nutation effects that would make astronomical navigation impossible for any hypothetical observers. The planet's rotational energy varies continuously as impacts either accelerate or decelerate the spinning proto-Earth, creating episodes where rotation might slow to near-synchronous rates with the orbital period, alternating with intervals of rapid spinning that compress the day-night cycle to a few hours. The chemical evolution of the magma ocean proceeds through a complex interplay between impact heating, which tends to homogenize the composition by maintaining everything in a molten state, and gravitational differentiation, which attempts to separate materials according to density and create distinct chemical layers. The balance between these competing processes shifts continuously as impact rates fluctuate, and the total thermal budget of the planet changes in response to the varying intensity of bombardment. During periods of particularly intense impact activity, the entire proto-Earth approaches chemical homogeneity as convection currents driven by impact heating mix materials from the surface down to depths of hundreds of kilometers. The surface morphology during this period lacks any recognizable geological features in the familiar sense, existing instead as a constantly changing landscape of overlapping impact craters in various stages of formation, cooling, and modification by subsequent impacts. The largest craters, created by the most massive impactors, remain visible as topographical features for thousands or tens of thousands of years before being obliterated by subsequent bombardment, creating a surface age measured not in millions or billions of years, but in the much shorter intervals between major impacts. This represents a fundamental difference from all later periods of Earth's geological history. When surface features persist for geological ages and allow the development of complex landscapes shaped by erosion, tectonics, and other gradual processes, the thermal evolution of the proto-Earth during this bombardment phase creates internal temperature gradients that will never be duplicated during later periods of planetary history, with the hottest regions often located near the surface where impact energy is deposited, and cooler zones existing in the deep interior where primitive materials retain some memory of the original cold conditions of the solar nebula. This temperature inversion drives convection patterns that operate in reverse compared to normal planetary interiors, with hot surface materials sinking into cooler depths, while cooler deep materials rise toward the increasingly hot surface, creating mixing processes that homogenize the chemical composition of the entire planet across timescales measured in millions of years. The bombardment intensity reaches a crescendo that represents the most violent period in Earth's entire history. A brief geological moment spanning perhaps only a few million years, when impact rates achieve levels that will never again be equaled during the remaining 4.5 billion years of planetary evolution. During this peak phase, major impacts occur not every few thousand years, as in the earlier stages of accretion, but every few hundred years, creating a nearly continuous state of global catastrophe where the planet exists in perpetual upheaval. The mathematical progression follows an exponential curve as the proto-Earth's gravitational cross-section expands, sweeping up material from an ever larger volume of space and accelerating its own growth through the inexorable logic of celestial mechanics. The largest impactors during this period represent the final generation of independent protoplanetary bodies, objects that have been growing through their own accretion processes for tens of millions of years, and have achieved masses comparable to modern dwarf planets before their orbital evolution finally brings them into collision with the dominant gravitational attractor that the proto-Earth has become. These encounters involve the collision of two partially differentiated worlds, each possessing its own core mantle structure, its own thermal history, and its own inventory of volatile compounds accumulated during the early phases of solar system formation. The energy released by such collisions approaches the theoretical limits of what solid matter can absorb without complete vaporization, creating impact events that fundamentally reshape not just the impact site, but the entire global structure of the proto-Earth. The shock waves generated by these planetary-scale collisions propagate through the proto-Earth's interior at velocities that approach the speed of sound in molten rock, carrying enough energy to trigger global-scale convection patterns that remix the entire magma ocean from surface to core mantle boundary. These seismic events represent earthquakes beyond any scale that will ever again occur on Earth, with magnitudes that would exceed 12 or 13 on the Richter scale, if such measurements were meaningful for a planet that lacks solid surface features capable of transmitting seismic waves in the conventional sense. The entire proto-Earth rings like a struck bell, though the sound propagates through molten rock rather than air, creating resonant frequencies that continue for thousands of years after each major impact. The scientific mystery embedded in this extreme bombardment involves the apparent impossibility of maintaining planetary coherence under such violent conditions. Yet somehow the proto-Earth not only survives but continues to grow throughout this period. Theoretical calculations suggest that impacts of this magnitude should fragment the planet entirely, dispersing its mass as debris throughout the inner solar system rather than contributing to continued accretion. The fact that planetary formation proceeds successfully despite these apparently destructive conditions implies the operation of physical processes that remain poorly understood even with modern computational modeling capabilities and theoretical frameworks. Current hypotheses focus on the role of the magma ocean itself as a shock-absorbing medium that can dissipate impact energy more efficiently than solid rock, preventing the catastrophic fracturing that would occur if similar impacts struck a fully solidified planet. The molten state of most of the proto-Earth's interior creates a fluid medium capable of flow and deformation on timescales much shorter than the intervals between major impacts, allowing the planet to heal and reintegrate between bombardment events. This represents a crucial feedback mechanism in planetary formation. The violence that threatens to destroy the growing world also maintains the molten conditions that enable it to survive that same violence. The atmospheric evolution during this peak bombardment period creates conditions that will never again exist anywhere in the solar system once planetary formation concludes. The continuous vaporization of surface materials by major impacts maintains an atmosphere composed almost entirely of rock vapor, at pressures and temperatures that approach the critical point where the distinction between gas and liquid phases disappears entirely. This supercritical rock vapor possesses properties unlike any material that exists under normal planetary conditions, with densities that vary continuously rather than exhibiting the sharp boundaries that characterize normal phase transitions. The greenhouse effect created by this rock vapor atmosphere drives surface temperatures to levels that exceed the melting points of virtually all naturally occurring materials, creating a planetary environment where tungsten would exist as a liquid and where even the most refractory compounds remain in a molten or gaseous state. The thermal radiation from this glowing planetary surface reaches intensities that would make the proto-Earth visible as a distinct reddish star from distances of several astronomical units, a beacon of planetary violence that announces the birth of a new world to any hypothetical observers elsewhere in the solar system. The magnetic field dynamics during this period reflect the complete chaos of the proto-Earth's interior, where convection patterns in the metallic core change on timescales measured in days or weeks, as major impacts continuously perturb the circulation patterns that generate planetary magnetism. The resulting magnetic field possesses no stable structure or orientation, consisting instead of rapidly fluctuating multipolar configurations that provide no meaningful protection against solar wind erosion. The interaction between this chaotic magnetic field and the dense rock vapor atmosphere creates electromagnetic phenomena unlike anything that will characterize later periods of Earth's history, including planetary-scale electrical discharges that transfer energy between the upper atmosphere and the surface at rates comparable to lightning storms covering entire continents. The rotational evolution of the proto-Earth during this bombardment phase becomes increasingly chaotic as major impacts impart angular momentum transfers that overwhelm the planet's rotational inertia. Some impacts occur at angles and velocities that significantly accelerate the planetary rotation, creating periods where the day-night cycle compresses to only a few hours and where centrifugal forces begin to affect the planet's overall shape, flattening it at the poles and bulging at the equator like a slowly spinning droplet of molten rock. Other impacts, particularly those that strike at oblique angles opposite to the direction of rotation, can slow or even temporarily reverse the planetary spin, creating episodes where the sun appears to rise in the west and set in the east. The chemical composition of the magma ocean undergoes its most dramatic evolution during this period. As the continuous input of impactor materials adds chemical components that were depleted or absent during the earlier phases of accretion. Many of the most massive impactors originate from regions of the solar system with different chemical compositions, bringing water ice from the outer asteroid belt, organic compounds from the realm of the forming gas giants, and metallic materials with isotopic signatures that reflect formation processes in different parts of the original solar nebula. This chemical mixing creates the first truly planetary-scale homogenization of materials in Earth's history, blending components from across the solar system into the unified chemical inventory that will eventually differentiate into the diverse minerals and rock types that characterize the modern Earth. The surface morphology during this peak bombardment consists entirely of overlapping impact features in various stages of formation and modification, creating a landscape that changes fundamentally every few hundred years as new impacts obliterate existing features and create entirely new topographical arrangements. The largest impact basins, created by the most massive impactors, achieve diameters measured in thousands of kilometers, creating temporary geological features comparable in scale to entire continents on the modern Earth. These impact basins fill with molten rock within days or weeks of their formation, creating vast lava lakes that persist for thousands of years before being disrupted by subsequent impacts. The thermal budget of the proto-Earth during this period approaches the theoretical maximum that solid matter can sustain, while maintaining gravitational coherence, creating internal temperatures that exceed the melting points of all known materials throughout the entire planetary interior from surface to core. This represents the closest approach to complete planetary melting that will occur during Earth's entire history, a state where the distinction between core, mantle, and crust disappears entirely, as all materials exist in various degrees of molten or gaseous states. The energy balance between impact heating and thermal radiation to space operates at the very limits of physical possibility, maintaining the proto-Earth just barely on the solid side of complete vaporization. The timescales that govern this peak bombardment compress the most transformative events in planetary formation into intervals brief enough that individual impacts can alter the fundamental character of the entire world within human comprehensible time spans. Yet the cumulative effects unfold across millions of years that stretch beyond easy imagination, creating a temporal paradox where planetary formation operates simultaneously on time scales both impossibly brief and impossibly long. The bombardment begins its gradual decline as the proto-Earth's gravitational dominance finally succeeds in clearing most of the solid debris from its orbital neighborhood, transforming the cluttered environment of the early solar system into something approaching the relatively empty space that characterizes the modern Earth-Moon system. This transition unfolds with the same geological patience that has marked all previous phases of planetary formation, yet represents a fundamental shift in the character of Earth's development, from violent construction through impact accretion to the more subtle processes of internal evolution and differentiation that will dominate the remaining billions of years of planetary history. The mathematical inevitability of this transition reflects the basic physics of gravitational dynamics, where larger objects inevitably capture or scatter smaller ones until orbital zones become gravitationally stable and largely debris-free. The interval between major impacts gradually lengthens from hundreds of years to thousands of years, then to tens of thousands of years, creating the first extended periods of relative stability in Earth's history, when surface features can persist long enough to be modified by processes other than catastrophic bombardment. This represents the beginning of geology in any recognizable sense, as the planet begins to develop surface characteristics that reflect internal processes rather than external violence. The impact craters that dominated earlier surface morphology begin to persist for longer periods, allowing the development of secondary features such as central peaks, terraced walls, and complex drainage patterns within crater basins that fill with cooling lava flows. The thermal evolution of the proto-Earth responds to this declining bombardment rate by beginning the slow transition from the extreme conditions of peak heating toward the more moderate internal temperatures that will eventually characterize the mature planet. The magma ocean, which has existed in a state of continuous turbulent convection, driven by constant impact heating, begins to stabilize its circulation patterns as the external energy input decreases and internal heat sources become more important relative to surface bombardment. This thermal transition creates the first opportunity for large-scale chemical differentiation to proceed without continuous disruption by impact-driven mixing, allowing the formation of distinct chemical layers that will eventually evolve into the core mantle crust structure of the modern Earth. The scientific mystery that emerges during this transition period involves the precise mechanisms by which the magma ocean begins to crystallize and solidify, transforming from a globally molten state to the differentiated structure of solid inner core, liquid outer core, solid mantle, and thin solid crust that characterizes today's Earth. Theoretical models suggest that this process should proceed from the bottom up, with crystallization beginning at the core mantle boundary where pressures are highest and working upward toward the surface, as heat loss to space gradually lowers internal temperatures. However, the complexity of multi-component chemical systems under extreme pressure and temperature conditions makes precise predictions difficult, and the actual sequence of crystallization events remains one of the most challenging problems in planetary science. Current understanding suggests that the transition begins with the formation of the first solid inner core, as iron-nickel alloy reaches pressures and temperatures where the solid phase becomes more stable than the liquid phase despite the extreme thermal conditions. This crystallization process releases latent heat of fusion that helps to drive continued convection in the surrounding liquid outer core, creating the first stable circulation patterns that will eventually generate Earth's permanent magnetic field. The formation of the solid inner core represents a crucial threshold in planetary evolution, marking the beginning of the internal structure that will enable the magnetic dynamo process, essential for protecting atmospheric evolution and the eventual development of life. The atmospheric composition during this declining bombardment period undergoes its most dramatic transformation since the beginning of accretion. As the continuous input of rock vapor from surface impacts decreases and thermal escape processes begin to remove the exotic high-temperature gases that have dominated the atmosphere during peak bombardment, silicon dioxide, magnesium oxide, and aluminum oxide, which have existed as gases during the most violent phases of planetary formation, begin to condense out of the atmosphere as surface temperatures drop below their respective condensation points, creating the first solid particles suspended in the gaseous envelope surrounding the proto-Earth. This atmospheric evolution creates weather systems unlike anything that will exist during later periods of Earth's history, with precipitation consisting of microscopic crystals of various rock-forming minerals rather than water droplets. Clouds of condensing silicate vapor drift through the upper atmosphere like metallic snow, occasionally producing rainfall events where tiny crystals of olivine, pyroxene, and feldspar settle toward the surface through the dense rock vapor that still dominates the lower atmospheric layers. These mineral precipitation events contribute to the first large-scale chemical differentiation of the planet's surface, as different minerals condense at different altitudes and temperatures, creating compositional variations that will eventually evolve into the diverse rock types that characterize terrestrial geology. The magnetic field generated by the proto-Earth during this transitional period begins to show the first signs of organizational structure as convection patterns in the liquid outer core stabilize in response to the more consistent thermal boundary conditions created by declining impact rates. Instead of the chaotic, rapidly fluctuating multipolar configurations that characterize the peak bombardment period, the magnetic field begins to develop quasi-stable dipolar components that occasionally align with the planetary rotation axis for extended periods measured in thousands of years. This magnetic stabilization represents the beginning of effective atmospheric protection against solar wind erosion, reducing the rate at which atmospheric gases escape to space and enabling the retention of increasingly substantial gaseous envelopes. The rotational dynamics of the proto-Earth continue to evolve as the planet approaches its final mass, and the frequency of major angular momentum transfer events decreases dramatically. The chaotic variations in day length that characterize the peak bombardment period begin to damp out as the planet's rotational inertia increases and the magnitude of individual impact perturbations becomes smaller relative to the total angular momentum of the system. The rotation rate gradually stabilizes around values that reflect the integrated effects of all previous impacts, creating the first consistent day-night cycles in Earth's history, though still much shorter than the 24-hour period that will eventually characterize the mature planet. The chemical evolution of the cooling magma ocean proceeds through a complex sequence of fractional crystallization events as different mineral phases reach their respective saturation points and begin to separate from the remaining liquid. The first minerals to crystallize are typically the most refractory compounds, those with the highest melting points, which form at the greatest depths where temperatures remain highest. These early crystallization products include various high-pressure phases of common rock-forming minerals that will be transformed into more familiar forms as the planet continues to cool and internal pressures stabilize. The surface morphology during this declining bombardment period begins to develop the first persistent geological features that will survive long enough to be modified by processes other than catastrophic impact events. Large impact basins created during the final phases of heavy bombardment begin to develop secondary features such as central uplift structures, concentric ring systems, and complex patterns of radial and circumferential fracturing that reflect the mechanical properties of the cooling surface materials. These impact basins serve as the first large-scale topographical features in Earth's history, creating elevation differences of several kilometers that will influence atmospheric circulation patterns and the eventual development of distinct climatic zones. The thermal budget of the proto-Earth during this transition period reflects the complex interplay between declining external energy input from impacts and the continuing internal heat sources created by radioactive decay, gravitational compression, and the latent heat released by ongoing crystallization processes. The surface temperatures begin their slow decline from the extreme values that characterize peak bombardment toward the more moderate levels that will eventually permit the existence of liquid water and the complex chemical processes necessary for life. This thermal evolution operates on timescales measured in millions of years, creating temperature gradients and heat flow patterns that will eventually drive the tectonic processes responsible for continental drift and mountain building. The atmospheric pressure during this period begins to stabilize as the balance between gas production from declining impact vaporization and gas loss through thermal escape reaches a quasi-steady state for the first time in Earth's history. The rock vapor that has dominated atmospheric composition during earlier periods gradually gives way to more conventional atmospheric gases as surface temperatures drop below the condensation points of most silicate compounds, creating the first atmospheric environment that bears some resemblance to the gas-dominated envelopes that characterize modern planetary atmospheres, though still at pressures and temperatures far beyond the range that will eventually support life. The first solid crust begins to form as surface temperatures drop below the melting points of the most refractory rock-forming minerals, creating isolated patches of crystalline material that float like scum on the surface of the global magma ocean. These initial crustal formations represent the earliest solid ground in Earth's history, though they bear little resemblance to the stable continental masses that will eventually characterize the mature planet's surface. Instead, they exist as thin, brittle shells of rapidly cooling rock that form and reform continuously as convection currents in the underlying magma ocean break them apart and drag them back into the molten interior, where they dissolve and mix with the surrounding liquid before rising again to create new crustal patches in an endless cycle of formation and destruction. The composition of this primitive crust reflects the chemical evolution of the magma ocean during the final phases of bombardment, dominated by minerals that crystallize at the highest temperatures and lowest pressures. Olivine, pyroxene, and calcic plagioclase feldspar form the primary constituents of these early crustal rocks, creating a composition similar to modern basalts, but with subtle differences that reflect the unique conditions of formation during the transition from molten to solid planetary states. The chemical signatures preserved in these primitive crustal materials will eventually provide crucial evidence for understanding the processes that operated during Earth's earliest history. Though most of these ancient rocks will be recycled through later geological processes and destroyed long before life develops the ability to study them. The scientific mystery embedded in early crustal formation involves the apparent paradox of how solid rock can form and persist on the surface of a planet that remains largely molten throughout most of its interior. Theoretical models suggest that the formation of stable crust requires not just appropriate surface temperatures, but also specific conditions of heat flow, chemical composition, and mechanical stability that are difficult to achieve during the dynamic conditions that characterize the late stages of planetary accretion. The fact that crustal formation proceeds successfully despite these challenges implies the operation of feedback mechanisms that stabilize surface conditions once initial crystallization begins. Current hypotheses focus on the role of thermal insulation provided by the newly formed crustal materials themselves, which possess much lower thermal conductivity than the molten rocks from which they crystallize. This creates a positive feedback loop where the formation of solid crust reduces heat loss from the underlying magma ocean, allowing surface temperatures to stabilize at levels that favor continued crystallization rather than remelting. The mathematical elegance of this process lies in its self-regulating character. Crustal formation creates the conditions necessary for more crustal formation, while crustal destruction through convective overturn creates the conditions necessary for renewed crystallization. The atmospheric composition continues its evolution toward more familiar chemical species, as the condensation of rock vapor removes the exotic high-temperature gases that dominated earlier atmospheric conditions. Water vapor, which has been present in trace quantities since the earlier stages of accretion, but remained overwhelmed by silicate gases during peak bombardment, begins to represent a more significant fraction of the total atmospheric mass as surface temperatures approach the stability range for this most crucial of all planetary volatiles, carbon dioxide. Another essential component of eventual atmospheric evolution also increases in relative abundance as the more exotic rock vapors condense out of the gaseous envelope. The pressure and temperature conditions in the evolving atmosphere approach the range where water vapor can theoretically condense into liquid droplets, though actual condensation remains impossible Due to the continued dominance of high-temperature conditions and the lack of appropriate nucleation sites in the exotic atmospheric chemistry that still characterizes this transitional period, the water vapor that does exist remains superheated well above its normal boiling point, creating atmospheric conditions that will persist for millions of years before surface temperatures drop enough to permit the first tentative experiments with liquid water formation. The magnetic field generated by the proto-Earth shows increasing signs of dipolar organization, as convection patterns in the liquid outer core respond to the more stable thermal boundary conditions created by the formation of solid inner core and the beginning of crustal development. The field strength increases gradually as the temperature difference between the core and the overlying mantle stabilizes, providing the thermal driving force necessary for sustained convective circulation in the electrically conductive metallic core material. This magnetic evolution represents the beginning of effective planetary protection against solar wind erosion, though the field remains much weaker and less stable than the robust dipolar configuration that will eventually characterize the mature Earth. The rotational evolution of the proto-Earth approaches a quasi-steady state as the frequency of major impacts decreases to levels where individual angular momentum transfer events no longer dominate the planet's rotational dynamics. The day length stabilizes around values significantly shorter than the modern 24-hour period, perhaps ranging from 6 to 12 hours depending on the integrated effects of all previous impact events and the final configuration of the planet's mass distribution. This rapid rotation creates pronounced equatorial bulging that affects atmospheric circulation patterns and contributes to the dynamic instability of the early crustal formations, as centrifugal forces work against gravitational forces to create complex stress patterns in the cooling surface materials. The chemical differentiation of the magma ocean proceeds through increasingly sophisticated fractional crystallization processes as the overall temperature of the system continues to decrease and different mineral phases reach their respective saturation points in the remaining liquid. The crystallization sequence follows the well-established principles of igneous petrology, with high-temperature minerals forming first and lower-temperature phases crystallizing from the progressively more evolved liquid compositions that remain after each episode of mineral separation. This process creates the first large-scale chemical heterogeneity in Earth's interior since the initial differentiation of metallic core from silicate mantle. The surface morphology during this early crustal formation period develops the first recognizable geological features that persist long enough to be modified by processes other than catastrophic destruction through impact bombardment or convective overturn. The cooling and crystallization of large impact basins creates elevated rim structures and complex central peak formations that represent the first mountains in Earth's history. Though these features remain small and temporary compared to the massive mountain ranges that will eventually be created by tectonic processes operating over much longer timescales. The thermal evolution of the planet during this crustal formation period creates the first stable temperature gradients that extend from the surface down through the crystallizing margins of the magma ocean to the still molten deep interior. These thermal gradients drive the first large-scale convection patterns that operate in partially solid materials rather than completely molten systems, creating the precursors to the mantle convection processes that will eventually drive plate tectonics and continental drift. The heat flow from the interior to the surface begins to stabilize around values that reflect the balance between internal heat production from radioactive decay and heat loss through thermal radiation to space. The atmospheric evolution during this period creates the first weather systems that operate through the interaction of different chemical species rather than the simple thermal expansion and contraction that characterized earlier atmospheric dynamics. The condensation of different mineral phases at different altitudes and temperatures creates atmospheric layering and circulation patterns that bear some resemblance to modern meteorological phenomena. Though operating with exotic chemical species and at pressure and temperature ranges far removed from any modern planetary environment. The timescales that govern early crustal formation operate at the intersection between the rapid processes of crystallization and cooling, which can proceed over thousands of years, and the much slower processes of large-scale chemical differentiation and thermal equilibration, which require millions of years to approach completion. This creates a temporal hierarchy where rapid surface changes occur against the background of slower, deep interior evolution, establishing the basic framework that will characterize geological processes throughout the remaining history of the planet. The gravitational field of the proto-Earth approaches its final configuration as the mass distribution stabilizes and the major episodes of accretionary growth conclude, creating the orbital environment that will eventually be populated by the Moon, and the complex system of gravitational interactions that will regulate Earth's rotational stability and climatic evolution over geological timescales. The cooling magma ocean begins to stratify into distinct chemical layers as fractional crystallization proceeds from the deepest levels toward the surface, creating the first permanent internal structure that will persist throughout the remaining billions of years of Earth's evolution. Dense, iron-rich minerals settle toward the bottom of the crystallizing zones, while lighter, silicon-rich compositions float toward the top, establishing the basic chemical gradients that will eventually differentiate into the familiar layers of core, mantle, and crust that characterize the modern planet. This stratification process operates through the patient working of density differences and gravitational settling, requiring millions of years to establish stable layering that can resist disruption by the convective circulation patterns that continue to operate in the remaining molten regions of the planetary interior. The first stable crustal patches grow larger and more persistent as surface temperatures continue their gradual decline and convective overturn becomes less vigorous in the upper levels of the magma ocean. These protocontinents represent islands of solid rock, floating on a global sea of molten material, creating the first recognizable geography in Earth's history, though one that remains highly dynamic and constantly changing as tectonic forces driven by mantle convection continuously reshape the surface configuration. The crustal materials themselves possess compositions that will never again be replicated during later periods of Earth's geological evolution, reflecting the unique chemical conditions that existed during the transition from global melting to solid surface formation. The atmospheric composition undergoes a fundamental transformation as water vapor begins to constitute a significant fraction of the total atmospheric mass for the first time since planetary formation began. The condensation of rock vapors removes most of the exotic high-temperature gases that have dominated atmospheric chemistry during earlier periods, allowing more familiar atmospheric species to emerge from the complex chemical background that has characterized the proto-Earth's gaseous envelope. Carbon dioxide increases in relative abundance as temperatures drop below its thermal decomposition point, while trace amounts of nitrogen, argon, and other noble gases begin to accumulate as the atmospheric retention efficiency improves with stronger magnetic field protection and lower thermal escape rates. The scientific mystery that emerges during this atmospheric transition involves the apparent impossibility of retaining substantial amounts of water vapor at the surface temperatures that still characterize this period of Earth's evolution. Theoretical calculations suggest that surface temperatures remain well above the critical point of water, making it thermodynamically impossible for liquid water to exist regardless of atmospheric pressure. Yet somehow the planet begins to accumulate and retain significant quantities of water vapor in its atmosphere, suggesting the operation of chemical or physical processes that are not accounted for in simple equilibrium models of high-temperature atmospheric chemistry. Current hypotheses propose that the key lies in the complex three-dimensional circulation patterns that develop in the cooling atmosphere, creating high-altitude regions where temperatures drop below the condensation point of water vapor, even though surface temperatures remain too high for liquid water stability. These atmospheric circulation cells transport water vapor from hot surface regions to cooler upper atmosphere zones, where it can condense into microscopic droplets that remain suspended as high-altitude clouds before evaporating again as they circulate back toward the warmer surface layers. This process creates a primitive water cycle that operates entirely in the vapor and cloud phases, without any liquid water reaching the planetary surface. The magnetic field evolution continues toward increasing dipolar organization, as thermal convection in the liquid outer core stabilizes around circulation patterns that align preferentially with the planetary rotation axis. The field strength approaches values that provide meaningful protection against solar wind erosion for the first time in Earth's history, reducing atmospheric escape rates by factors of 10 or more compared to the completely unprotected conditions that characterized earlier periods. This magnetic protection enables the retention of atmospheric components that would otherwise be stripped away by charged particle bombardment from the young sun, allowing the development of more complex atmospheric chemistry and the accumulation of volatile species essential for eventual biological evolution. The rotational dynamics of the proto-Earth stabilize around a configuration that reflects the integrated effects of all the angular momentum transfer events that have occurred during the accretion process, creating a rotation period significantly shorter than the modern 24-hour day, but much more stable than the chaotic variations that characterize the peak bombardment period. The rapid rotation creates strong Coriolis effects that influence atmospheric circulation patterns and contribute to the complex three-dimensional fluid dynamics that characterize both the atmosphere and the remaining molten regions of the planetary interior. These rotational effects will play crucial roles in establishing the circulation patterns that eventually drive weather systems and ocean currents once liquid water becomes possible. The chemical evolution of the crystallizing magma ocean creates increasingly sophisticated mineral assemblages as temperature and pressure conditions approach the ranges where common rock-forming minerals achieve their stable configurations. The crystallization sequence produces layered structures where different mineral phases dominate at different depths, creating the first large-scale chemical heterogeneity in Earth's interior since the initial separation of metallic core from silicate mantle. These mineral layers will eventually be disrupted and mixed by later convective processes, but they establish the basic chemical framework that will influence igneous processes throughout the remaining history of the planet. The surface morphology develops increasing complexity as the growing crustal patches begin to interact with each other through the tectonic forces generated by underlying mantle convection. The first collisions between crustal fragments create elevated regions that represent the ancestors of mountain ranges, though these early topographical features remain modest in scale compared to the massive continental structures that will eventually be created by plate tectonic processes operating over hundreds of millions of years. The early crustal collisions also create the first rift systems where divergent motion pulls crustal fragments apart, establishing the basic patterns of extensional and compressional tectonics that will characterize later geological evolution. The thermal budget of the planet approaches a configuration where internal heat production from radioactive decay begins to rival impact heating as the dominant energy source driving geological processes. This transition marks the beginning of the long-term thermal evolution that will characterize the mature Earth, where internal energy sources maintain convective circulation in the mantle and drive tectonic processes at the surface. The heat flow patterns established during this transitional period create the temperature gradients that will eventually enable the complex geochemical processes necessary for the formation of diverse rock types and the establishment of habitable surface conditions. The atmospheric pressure begins to stabilize around values that reflect the balance between outgassing from the cooling surface materials and loss processes such as thermal escape and solar wind erosion. The pressure remains much higher than will eventually characterize the mature Earth's atmosphere, reflecting the continued outgassing of volatile components from the crystallizing magma ocean and the relatively inefficient atmospheric loss processes that operate under the high temperature conditions that still prevail. This atmospheric pressure evolution creates the first quasi-stable boundary conditions that will eventually enable the development of more complex atmospheric chemistry and circulation patterns. The timescales governing this crystallization and stabilization period operate at the intersection between rapid surface processes, which can produce visible changes over periods of thousands of years, and slow internal processes, which require millions of years to establish stable configurations. This temporal hierarchy creates a complex geological environment where surface features form and evolve rapidly, while deep interior structures develop much more gradually, establishing the basic framework that will characterize Earth's geological processes throughout its remaining history. The gravitational interactions between the proto-Earth and other objects in the solar system begin to approach their final configuration as the major phases of planetary accretion conclude throughout the inner solar system, creating the orbital dynamics that will eventually regulate climate evolution and maintain the stable conditions necessary for the development and preservation of complex life over geological timescales. The temperature of the proto-Earth surface approaches the critical threshold where water vapor can theoretically condense into liquid droplets for the first time in planetary history, though the actual formation of stable liquid water remains frustrated by the complex atmospheric chemistry that still characterizes this transitional period. Surface temperatures have dropped from the extreme values that characterized peak bombardment, where rocks glowed white-hot and metals existed as vapors, to more moderate levels where common silicate minerals can maintain their solid crystalline structures for extended periods. Yet even these reduced temperatures remain hundreds of degrees above the boiling point of water under normal atmospheric pressure conditions, creating an environment where liquid water exists only as a theoretical possibility rather than a physical reality. The atmospheric composition during this period develops increasing complexity as multiple chemical species achieve significant concentrations simultaneously for the first time since planetary formation began. Water vapor constitutes perhaps 10 to 20% of the total atmospheric mass, while carbon dioxide represents another substantial fraction, creating the foundation for the greenhouse effect that will eventually regulate planetary climate throughout the remaining billions of years of Earth's evolution. Nitrogen begins to accumulate as a major atmospheric component, outgassed from the cooling crustal materials and retained more efficiently due to improved magnetic field protection against solar wind erosion. Trace amounts of noble gases, particularly argon and neon, provide chemical fingerprints that will eventually allow planetary scientists to reconstruct the early atmospheric evolution through isotopic analysis of ancient rocks. The scientific mystery that dominates this period involves the apparent paradox of how an atmosphere rich in water vapor can exist in equilibrium with surface temperatures that remain far above the critical point of water. According to basic thermodynamic principles, water should exist only as a supercritical fluid under these conditions, neither truly liquid nor truly gaseous, but possessing properties intermediate between the two states. Yet observational evidence from this period, preserved in the chemical signatures of the oldest terrestrial rocks, suggests that water vapor behaves as a distinct atmospheric component with properties similar to normal gas phase water, implying the operation of physical or chemical processes that are not predicted by simple equilibrium thermodynamics. Current theoretical models propose that the solution lies in the complex vertical structure that develops in the evolving atmosphere, where rapid vertical mixing creates temperature gradients steep enough that water vapor can condense in the upper atmosphere, even though surface temperatures remain too high for liquid water stability. These atmospheric temperature inversions, driven by convective circulation patterns that transport heat from the hot surface to the cooler upper atmosphere, create distinct atmospheric layers where different chemical species dominate and where phase transitions can occur under conditions that would be impossible in a well-mixed atmospheric system. The magnetic field strength continues to increase as thermal convection in the liquid outer core achieves the organized circulation patterns necessary for efficient magnetic dynamo operation. The dipolar component of the field begins to dominate over the chaotic multipolar contributions that characterized earlier periods, creating a magnetic configuration that provides increasingly effective protection against charged particle bombardment from space. This magnetic evolution enables the retention of atmospheric components that would otherwise be lost through solar wind stripping, particularly the lighter elements such as hydrogen and helium that will eventually play crucial roles in atmospheric chemistry and climate regulation. The crustal formation process achieves its first major milestone as interconnected patches of solid rock begin to cover substantial fractions of the planetary surface, creating the first quasi-continuous solid crust in Earth's history. These crustal materials remain thin and mechanically weak compared to the massive continental plates that will eventually characterize the mature Earth, but they represent a fundamental transition from a planet dominated by molten surfaces to one where solid rock provides the primary interface between the interior and the atmosphere. The composition of this primitive crust reflects the chemical evolution of the crystallizing magma ocean, dominated by mafic minerals rich in magnesium and iron that will eventually be reworked through igneous and metamorphic processes to create the more diverse rock types that characterize modern continental geology. The tectonic processes that operate during this early crustal formation period bear little resemblance to the organized plate tectonic system that will eventually drive continental drift and mountain building processes. Instead, crustal deformation occurs through chaotic patterns of compression and extension, driven by the convective circulation in the underlying magma ocean, creating complex networks of fractures, ridges, and basins that form and evolve on timescales measured in thousands rather than millions of years. These primitive tectonic processes establish the basic mechanical principles that will eventually evolve into the sophisticated plate boundary interactions that characterize modern geological dynamics. The atmospheric circulation patterns develop increasing sophistication as the cooling surface creates larger temperature contrasts and the strengthening Coriolis effects due to rapid planetary rotation drive more complex three-dimensional flow patterns. These circulation systems transport heat, moisture, and chemical species between different regions of the planet, creating the first large-scale atmospheric mixing processes that homogenize atmospheric composition on global scales. The circulation patterns also transport volcanic gases and other surface emissions to higher altitudes, where they can participate in photochemical reactions driven by solar ultraviolet radiation, beginning the complex atmospheric chemistry that will eventually produce the oxygen-rich atmosphere necessary for complex life. The volcanic activity that characterizes this period operates under conditions unlike anything that will exist during later periods of Earth's geological evolution, with magma compositions that reflect the unique chemistry of the crystallizing global magma ocean, rather than the more localized melting processes that will drive later volcanic systems. These early volcanoes produce vast outpourings of basaltic lava that flood large regions of the newly formed crust, creating the first large-scale igneous provinces in Earth's history. The volcanic emissions also contribute significant quantities of water vapor, carbon dioxide, sulfur compounds, and other atmospheric gases that will play crucial roles in establishing the chemical conditions necessary for eventual biological evolution. The thermal evolution of the planet during this period creates the first stable geothermal gradients that extend from the surface through the crystallizing crustal materials down to the still molten regions of the deep interior. These temperature gradients drive the first large-scale heat flow patterns that will eventually power the convective processes responsible for plate tectonics and continental drift. The geothermal energy flux from the interior to the surface remains much higher than will characterize the mature Earth, reflecting the continued cooling of the planet from its initial molten state and the ongoing heat production from the decay of short-lived radioactive isotopes that were incorporated during the accretion process. The chemical weathering processes that operate under the high-temperature high humidity conditions of this early atmospheric environment create the first large-scale alteration of crustal materials through interaction with atmospheric gases and water vapor. Although liquid water remains absent from the surface, the chemical reactivity of water vapor at high temperatures enables significant rock-atmosphere interactions that begin the slow process of chemical differentiation that will eventually create the diverse mineral assemblages that characterize sedimentary and metamorphic rocks. These early weathering processes also begin the global geochemical cycles that will eventually regulate atmospheric composition and climate over geological timescales. The timescales that govern this transitional period reflect the complex interplay between rapid surface processes, such as volcanic eruptions and atmospheric circulation changes that can occur over periods of years to centuries, and slower deep interior processes, such as continued crystallization of the magma ocean and establishment of stable thermal gradients that require thousands to millions of years to approach equilibrium. This temporal complexity creates a dynamic planetary environment where surface conditions evolve rapidly while fundamental planetary structure develops more gradually, establishing the framework for the even more complex interactions between geological and biological processes that will eventually characterize the mature Earth system. The first tentative experiments with liquid water formation begin as atmospheric circulation patterns create localized regions where temperature and pressure conditions briefly achieve the narrow range necessary for water vapor condensation. Though these liquid water droplets remain suspended in the atmosphere as microscopic particles that evaporate almost immediately upon contact with the still hot surface materials, these ephemeral water droplets represent the earliest liquid water in Earth's history, existing for perhaps minutes or hours before returning to the vapor phase, yet marking a crucial threshold in planetary evolution where the chemical and physical conditions necessary for life begin to emerge from the extreme environment that has characterized the proto-Earth since its formation. The formation and immediate destruction of these liquid water droplets creates the first true water cycle in Earth's history, operating entirely within the atmospheric system through evaporation and condensation processes that transport water between different altitude levels and temperature zones. the atmospheric pressure stabilizes around values approximately 10 times higher than modern sea level pressure, creating a dense gaseous envelope that can support complex circulation patterns and enable more efficient heat transport between different regions of the planet. The high-pressure atmosphere also shifts the thermodynamic equilibrium conditions for water, raising the boiling point to temperatures that approach the cooling surface conditions and creating a narrow window where liquid water droplets can exist in the atmosphere, even though surface temperatures remain too high for stable liquid water bodies. The pressure-temperature relationship follows the basic principles of phase diagram thermodynamics, but the specific conditions that exist during this transitional period create unusual opportunities for water phase transitions that will not be replicated during later periods of Earth's evolution. The magnetic field achieves its first stable dipolar configuration as convection in the liquid outer core organizes around circulation patterns that align consistently with the planetary rotation axis, creating a magnetic moment comparable to perhaps half the strength of the modern Earth's magnetic field. This magnetic protection dramatically reduces the rate of atmospheric escape through solar wind erosion, enabling the retention of light elements such as hydrogen that would otherwise be stripped away by charged particle bombardment from the young sun. The magnetic field evolution also creates the first magnetosphere, a region of space around Earth where planetary magnetic forces dominate over the magnetic fields carried by the solar wind, establishing the protective magnetic environment that will eventually enable the preservation of complex atmospheric chemistry necessary for biological processes. The scientific mystery that emerges during this water formation period involves the apparent impossibility of explaining how liquid water droplets can form and persist even briefly under the atmospheric conditions that characterize this transitional period. Theoretical models of high-temperature atmospheric chemistry suggest that water should exist only as a highly reactive supercritical fluid that rapidly dissociates into hydrogen and oxygen under the influence of intense solar ultraviolet radiation and high thermal energy. Yet chemical evidence preserved in the oldest terrestrial rocks indicates that liquid water droplets not only formed but participated in chemical reactions that created hydrated mineral phases, implying that water maintained its molecular integrity for periods long enough to engage in complex geochemical processes. Current hypotheses focus on the possibility that atmospheric circulation patterns create microenvironments where rapid cooling and high local humidity enable water droplet formation and brief stabilization before the droplets are transported back into higher temperature regions where they evaporate or dissociate. These atmospheric microenvironments might exist within convective cells, where rising moist air cools rapidly as it expands at higher altitudes, creating temporary zones of water saturation that persist for hours or days before atmospheric mixing homogenizes the temperature and humidity conditions. The mathematical complexity of modeling these three-dimensional atmospheric dynamics under the extreme conditions that characterize this period makes precise predictions difficult, leaving the mechanisms of early water formation as one of the most challenging problems in early Earth science. The crustal evolution accelerates as the interconnected patches of solid rock achieve sufficient thickness and mechanical strength to support their own weight without continuous deformation through viscous flow processes. This represents the formation of the first truly rigid surface materials in Earth's history, creating platforms capable of supporting topographical features that persist for extended periods and enabling the development of more complex geological structures through tectonic processes. The crustal thickness remains modest compared to modern continental crust, perhaps ranging from 1 to 5 kilometers in most regions, but sufficient to create distinct mechanical boundaries between the solid surface and the underlying partially molten materials. The volcanic processes that operate during this period achieve unprecedented scales, as the pressure release associated with crustal formation triggers massive eruptions that dwarf any volcanic activity that will occur during later periods of Earth's history. These eruptions release vast quantities of magma that have been accumulating pressure during the gradual crystallization of the global magma ocean, creating flood basalt provinces that cover areas comparable to entire modern continents. The volcanic emissions also contribute enormous quantities of atmospheric gases, including water vapor, carbon dioxide, sulfur dioxide, and hydrogen sulfide, that dramatically alter atmospheric composition and create the chemical conditions necessary for the next phase of planetary evolution. The atmospheric chemistry develops increasing complexity as the diverse volcanic emissions interact with each other and with solar radiation to create the first large-scale photochemical processes in Earth's atmosphere. Ultraviolet radiation from the young sun drives chemical reactions that break apart simple molecules and create more complex compounds, beginning the atmospheric chemistry that will eventually produce the oxygen-rich environment necessary for complex life. The photochemical processes also create the first atmospheric ozone, though in concentrations far too low to provide meaningful protection against ultraviolet radiation, beginning the slow development of the stratospheric ozone layer that will eventually shield the surface from harmful radiation. The thermal evolution of the planetary interior approaches a quasi-steady state as the rate of internal heat production from radioactive decay begins to balance the rate of heat loss through surface radiation and atmospheric transport processes. This thermal equilibrium creates stable temperature gradients that enable the development of organized convection patterns in the mantle, establishing the thermal driving forces that will eventually power plate tectonic processes and maintain geological activity throughout the remaining billions of years of Earth's evolution. The geothermal heat flow remains much higher than will characterize the mature Earth, but begins to approach values that can sustain complex geological processes without the continuous extreme heating that characterized earlier periods. The rotational evolution of the planet stabilizes around a configuration where the day length approaches perhaps 8 to 12 hours, significantly shorter than the modern 24-hour period, but much more stable than the chaotic variations that characterize the accretion period. This rapid rotation creates strong atmospheric circulation patterns, driven by Coriolis effects, and contributes to the development of the first organized weather systems that transport heat, moisture, and atmospheric gases between different climatic zones. The rotational stability also enables the development of more predictable tidal effects that will eventually play important roles in coastal erosion and oceanic circulation once liquid water oceans become possible. The chemical differentiation of the planet's interior proceeds through increasingly sophisticated processes as different mineral phases achieve their stable configurations under the pressure and temperature conditions that characterize the cooling planetary interior. The formation of distinct chemical layers creates compositional gradients that will drive convective mixing processes and establish the geochemical cycles that will eventually regulate the exchange of elements between the interior surface and atmosphere. These early differentiation processes create the chemical reservoirs that will supply the diverse rock types and mineral assemblages that characterize modern geological systems. The time scales that govern this water formation period operate at the intersection between rapid atmospheric processes that can create and destroy water droplets over periods of minutes to hours, and slower planetary cooling processes that gradually shift the overall temperature and pressure conditions toward ranges where liquid water becomes increasingly stable. This temporal complexity creates a dynamic environment where brief episodes of liquid water formation occur against the background of continued planetary cooling, establishing the conditions that will eventually enable the formation of permanent water bodies and the development of the hydrosphere that will characterize the mature Earth system. The surface temperature of the proto-Earth crosses the critical threshold where liquid water can theoretically exist in stable contact with solid rock for the first time in planetary history, though the actual formation of persistent water bodies remains elusive due to the complex interplay between atmospheric pressure, local temperature variations, and the continued volcanic outgassing that maintains atmospheric compositions hostile to liquid water stability. The global average surface temperature approaches 374 degrees Celsius, the critical point of pure water, creating conditions where the distinction between liquid and vapor phases begins to blur, and where small variations in local pressure or temperature can tip the balance between water existing as a dense vapor or as a true liquid. These borderline conditions create a planetary environment unlike anything that exists in the modern solar system, where water hovers perpetually on the edge of phase transition, occasionally condensing into brief liquid pools that evaporate within hours or days of their formation. The atmospheric composition achieves a complexity that will not be matched again until the development of oxygen-producing photosynthesis billions of years in the future. With water vapor, carbon dioxide, nitrogen, sulfur compounds, and trace amounts of numerous other chemical species creating a dense, chemically reactive gaseous envelope that participates actively in geological processes through chemical weathering and atmospheric surface interactions. The partial pressure of water vapor approaches saturation levels for the first time, creating humidity conditions where atmospheric water can condense not just in high-altitude clouds, but occasionally at the surface itself, particularly in regions where local topography or atmospheric circulation patterns create slightly cooler microclimates. These localized condensation events represent the first tentative steps toward the formation of a permanent hydrosphere, though the condensed water remains highly unstable and prone to rapid re-evaporation. The volcanic activity that characterizes this period achieves its maximum intensity as the final crystallization of the global magma ocean releases the last substantial volumes of magma that have been accumulating pressure since the earliest stages of planetary formation. These massive volcanic eruptions create temporary atmospheric loading with volcanic gases that can briefly shift local atmospheric chemistry, enough to enable liquid water formation in the immediate vicinity of volcanic vents, where rapid cooling of water-rich volcanic emissions creates the first volcanic lakes in Earth's history. These volcanic water bodies exist for perhaps months or years before evaporating completely, but they represent crucial experiments in surface water chemistry that establish the basic principles governing water-rock interactions under high-temperature conditions. The scientific mystery that dominates this critical threshold period involves the apparent contradiction between thermodynamic models that predict water instability under the pressure and temperature conditions that characterize this period, and geological evidence preserved in ancient rock formations that clearly indicates the occurrence of liquid-water interactions with surface materials, hydrated mineral phases that can form only through direct contact with liquid water begin to appear in the geological record during this period. Yet the environmental conditions should theoretically prevent liquid water from existing for periods long enough to drive the chemical reactions necessary for hydrated mineral formation. This discrepancy suggests that either the thermodynamic models fail to account for important chemical or physical processes, or that local environmental conditions differ dramatically from global average conditions. Current theoretical approaches focus on the possibility that rapid atmospheric circulation patterns create persistent microenvironments where temperature and pressure conditions remain within the narrow range necessary for liquid water stability, even though global conditions remain marginal for water formation. These atmospheric circulation cells might transport water vapor from hot regions to cooler areas fast enough that local cooling can drive condensation before atmospheric mixing can re-equilibrate the temperature and humidity conditions. The mathematical modeling of these complex three-dimensional circulation patterns under the extreme atmospheric conditions that characterize this period requires computational resources that push the limits of current supercomputing capabilities, making detailed predictions difficult and leaving many aspects of early water formation as open scientific questions. The magnetic field evolution reaches a crucial milestone as the organized circulation patterns in the liquid outer core achieve sufficient stability and intensity to generate a dipolar magnetic moment comparable to perhaps 75% of the modern Earth's magnetic field strength. This magnetic protection creates the first truly effective barrier against solar wind erosion of atmospheric components, reducing the rate of atmospheric escape by factors of 100 or more compared to the unprotected conditions that characterized earlier periods. The magnetic field protection enables the retention of light atmospheric constituents, particularly hydrogen, that would otherwise be stripped away by charged particle bombardment, allowing the development of more complex atmospheric chemistry and creating the conditions necessary for water vapor to achieve saturation levels in the atmosphere. The crustal formation process achieves near global coverage as the final patches of exposed magma ocean surface become covered by thin layers of crystallized rock, creating the first continuous solid crust in Earth's history. This crustal shell remains mechanically weak and highly fractured compared to modern continental or oceanic crust, but it provides a solid interface between the planetary interior and the atmosphere that enables more complex geological processes to operate. The crustal composition reflects the chemical evolution of the crystallizing magma ocean, creating a global basement of mafic igneous rocks that will serve as the foundation for all subsequent geological evolution. The tectonic processes that operate during this crustal completion period create the first large-scale structural features that will persist long enough to influence subsequent geological evolution, including linear zones of crustal weakness that will eventually evolve into the first rift systems and the elevated regions that represent the precursors to mountain ranges. These early tectonic features remain modest in scale, compared to the massive structural systems that will eventually characterize plate tectonic processes, but they establish the basic patterns of crustal deformation that will guide later geological development. The tectonic activity also creates the first substantial topographical relief on the planetary surface, with elevation differences of several kilometers that will influence atmospheric circulation patterns and create the first distinct climatic zones. The atmospheric pressure begins to stabilize around values that reflect the balance between continued outgassing from the cooling planetary interior and the increasing efficiency of atmospheric retention due to magnetic field protection and lower thermal escape rates. The pressure stabilizes at approximately 8 to 12 times modern sea level pressure, creating atmospheric density conditions that significantly affect the thermodynamic properties of water and other atmospheric constituents. This high atmospheric pressure shifts the boiling point of water to temperatures that approach the cooling surface conditions, creating a narrow window where liquid water can exist at the surface under favorable local conditions. The chemical weathering processes that operate under the high temperature, high pressure atmospheric conditions of this period create the first large-scale alteration of crustal rocks through interaction with atmospheric water vapor and other reactive gases. Although most of these weathering reactions occur in the vapor phase rather than through direct contact with liquid water, they begin the process of chemical differentiation that will eventually create the diverse mineral assemblages and rock types that characterize the modern Earth's surface. The weathering products also contribute to atmospheric chemistry by releasing additional water vapor, carbon dioxide, and other gases that participate in the complex atmospheric chemical cycles that will eventually regulate planetary climate. The thermal evolution of the planet approaches a configuration where the rate of internal heat production begins to match the rate of heat loss through surface radiation and atmospheric transport, creating the first quasi-steady thermal state in Earth's history. This thermal equilibrium enables the development of stable convection patterns in the mantle that will eventually drive plate tectonic processes, while maintaining surface temperatures that approach the range where liquid water can exist stably. The geothermal heat flow remains elevated compared to modern values, but begins to approach levels that will characterize the mature Earth system. The timescales that govern this critical threshold period reflect the complex interplay between rapid atmospheric and surface processes that can shift water between vapor and liquid phases over periods of hours to days, and slower planetary cooling and atmospheric evolution processes that gradually move the overall system toward conditions where liquid water becomes increasingly stable over periods of thousands to millions of years. This temporal complexity creates a dynamic planetary environment where the fundamental character of surface conditions evolves gradually while specific water formation events occur rapidly and unpredictably. The first permanent pools of liquid water begin to form in the deepest topographical depressions of the newly formed crustal surface, creating the earliest lakes in Earth's history. Though these water bodies remain small, shallow, and highly ephemeral compared to the vast hydrological systems that will eventually characterize the mature planet. These primordial lakes exist in a state of constant dynamic equilibrium between evaporation and condensation, their water levels fluctuating dramatically in response to local atmospheric conditions, volcanic activity, and the gradual planetary cooling that slowly shifts the global balance toward increasingly favorable conditions for liquid water stability. The water in these early lakes possesses chemical compositions unlike any natural water that will exist during later periods of Earth's history, heavily loaded with dissolved volcanic gases, metallic ions leached from the hot crustal rocks, and exotic chemical species that reflect the extreme atmospheric conditions under which the water originally condensed. The atmospheric water vapor finally achieves true saturation conditions on a global scale, creating the first substantial cloud systems that persist for extended periods and participate in organized meteorological processes rather than existing as brief, localized condensation events. These early cloud formations consist of water droplets mixed with condensed volcanic gases and microscopic particles of silicate dust, creating atmospheric optical properties that filter and scatter solar radiation in ways that will never be replicated once atmospheric composition evolves toward more familiar chemical mixtures. The cloud systems also begin to participate in large-scale heat transport processes, moving thermal energy from warmer equatorial regions toward cooler polar areas and establishing the first global atmospheric circulation patterns that will eventually evolve into the complex weather systems that characterize modern planetary climates. The volcanic outgassing reaches its final major episode as the last substantial volumes of magma remaining from the global magma ocean crystallization process find their way to the surface through the fracture systems created by ongoing crustal formation and tectonic adjustment. These ultimate volcanic eruptions release enormous quantities of water vapor that have been trapped in the crystallizing magma for millions of years, adding the final major contribution to atmospheric water content and pushing the global water vapor inventory past the threshold necessary for sustained liquid water formation. The volcanic emissions also include substantial amounts of carbon dioxide, nitrogen, sulfur compounds, and trace amounts of numerous other atmospheric gases that create the complex atmospheric chemistry necessary for the next phase of planetary evolution. The scientific mystery that characterizes this final transition to permanent water formation involves the apparent paradox of how liquid water bodies can maintain their existence despite surface temperatures that still occasionally exceed the boiling point of water under the prevailing atmospheric pressure conditions. Geological evidence indicates that some of these early lakes persisted for thousands or tens of thousands of years, periods long enough for complex chemical reactions to occur between liquid water and crustal rocks. Yet theoretical models suggest that even minor increases in local temperature should cause complete evaporation of any liquid water bodies. This discrepancy implies the operation of stabilizing mechanisms that are not accounted for in simple equilibrium models of water-atmosphere interactions. Current hypotheses focus on the possibility that the high atmospheric pressure and dense water vapor content create microenvironmental conditions where liquid water can exist metastably at temperatures above its normal boiling point, similar to the superheating effects that can occur in very pure water under carefully controlled laboratory conditions. The dense atmospheric water vapor might also create local humidity conditions that suppress evaporation rates enough to allow liquid water bodies to persist even when ambient temperatures exceed normal boiling points. Additionally, the rapid circulation of atmospheric water vapor between liquid and vapor phases might create local cooling effects through latent heat absorption that stabilize liquid water temperatures below the critical threshold for complete evaporation. The magnetic field achieves its mature configuration as convection patterns in the liquid outer core stabilize around the circulation geometry that will characterize the modern geodynamo, creating a dipolar magnetic moment that approaches the full strength of the present-day Earth's magnetic field. This magnetic protection provides complete shielding against solar wind erosion of atmospheric components, enabling the retention of even the lightest atmospheric constituents and allowing the development of the complex atmospheric chemistry that will eventually support biological processes. The stable magnetic field also creates the first persistent magnetosphere, establishing the protective magnetic environment that will enable the preservation of surface water bodies against space weather events and charged particle bombardment. The crustal evolution enters its final phase as the thin, fractured shell of crystallized rock that covers the planetary surface begins to thicken and achieve the mechanical strength necessary to support substantial topographical features and resist deformation by the convective processes operating in the underlying mantle. The crustal composition evolves toward more differentiated rock types as ongoing volcanic processes and chemical weathering begin to create the diversity of igneous, sedimentary, and metamorphic rocks that will characterize later geological periods. The crustal thickness approaches values comparable to modern oceanic crust in most regions, though still much thinner than the continental crust that will eventually be created through billions of years of additional geological evolution. The atmospheric composition stabilizes around a mixture dominated by water vapor, carbon dioxide, and nitrogen, with trace amounts of noble gases and other chemical species that will provide the foundation for all subsequent atmospheric evolution. The atmospheric pressure stabilizes around values approximately 10 times higher than modern sea level pressure, creating atmospheric density conditions that will persist for hundreds of millions of years before gradual atmospheric escape and evolving geological processes slowly reduce atmospheric mass toward more familiar levels. The atmospheric chemistry achieves sufficient complexity to support the first large-scale photochemical processes that will eventually lead to oxygen production and the development of the oxygen-rich atmosphere necessary for complex life, the thermal evolution of the planet approaches final equilibrium as the rate of heat loss through surface radiation and atmospheric transport balances the continuing heat production from radioactive decay in the planetary interior, creating stable thermal conditions that will characterize the mature Earth system. Surface temperatures stabilize in the range where liquid water can exist permanently over large areas of the planetary surface, though still much warmer than the moderate temperatures that will eventually enable the development of complex ecosystems. The geothermal heat flow approaches values that will drive plate tectonic processes throughout the remaining history of the planet, establishing the thermal engine that will power continental drift, mountain building, and volcanic activity for billions of years. The hydrological cycle achieves its first stable configuration as evaporation from the growing lake systems provides water vapor that condenses in the atmosphere and returns to the surface as the first true precipitation in Earth's history. This primitive water cycle operates under chemical and physical conditions that will never again exist on Earth, with precipitation consisting of highly acidic water loaded with dissolved volcanic gases and occurring under atmospheric pressure and temperature conditions that create unusual precipitation mechanisms and surface water chemistry. The establishment of a functioning hydrological cycle marks the beginning of the complex interactions between atmospheric, hydrological, and geological processes that will eventually create the integrated Earth system capable of supporting life. The chemical weathering processes accelerate dramatically as liquid water finally becomes available to participate directly in rock-water interactions, creating the first large-scale chemical alteration of crustal materials through liquid phase reactions rather than the vapor phase processes that characterized earlier periods. These weathering reactions begin the process of soil formation and create the first substantial transport of dissolved chemical species from crustal rocks into surface water bodies, establishing the geochemical cycles that will eventually regulate atmospheric composition and oceanic chemistry. The weathering processes also begin to consume atmospheric carbon dioxide through carbonate formation reactions, establishing the first negative feedback mechanisms that will eventually help stabilize planetary climate over geological timescales. The timescales that govern this final transition to permanent water formation reflect the achievement of stable equilibrium between multiple planetary systems operating on different temporal scales, from rapid hydrological processes that cycle water between atmospheric and surface reservoirs over periods of days to years, to slower geological processes that continue to modify crustal composition and internal thermal structure over periods of millions of years. This temporal integration creates the first truly stable planetary environment in Earth's history, establishing the foundation for the complex geological, atmospheric, and hydrological interactions that will eventually enable the development and evolution of life. The last major impacts of the Hadean bombardment arrive like final punctuation marks in a violent geological sentence that has been written across tens of millions of years, each collision now representing not the routine destruction that characterized earlier periods, but exceptional events that disrupt an increasingly stable planetary surface for the final time before Earth settles into the more predictable rhythms of geological evolution that will characterize the remaining 4 billion years of its history. These ultimate impacts strike a world that has become almost unrecognizably different from the molten, chaotic proto-planet that began this transformative period, colliding with solid crustal materials that can preserve the scars of impact rather than simply absorbing the energy into an already molten surface, creating the first permanent geological features that will survive long enough to be buried by sediments and preserved in the geological record for future study by conscious minds that will not emerge for billions of years The impact craters created by these final bombardment events achieve diameters measured in hundreds of kilometers, comparable to the largest impact structures that will ever be created during the subsequent history of the solar system, forming massive circular basins that collect the first substantial volumes of liquid water and create the earliest large lakes in Earth's history. These impact-generated water bodies represent a profound irony in planetary formation. The same violent processes that have threatened to destroy the emerging world now create the topographical depressions necessary for water accumulation and the formation of the first stable aquatic environments. The water that fills these impact basins carries dissolved materials leached from the shocked and fractured rocks surrounding the impact sites, creating chemical compositions that will never again be replicated in terrestrial surface waters. The atmospheric response to these final major impacts creates the last episodes of global atmospheric disruption in Earth's history, as the vaporization of crustal materials and any surface water bodies temporarily loads the atmosphere with rock vapor and superheated steam that briefly returns atmospheric conditions to something resembling the extreme environments that characterized peak bombardment millions of years earlier. These atmospheric perturbations persist for thousands of years after each impact, creating global climate disruptions that alternate between periods of extreme heating due to rock vapor, greenhouse effects, and subsequent cooling as the vaporized materials condense out of the atmosphere and return to the surface as exotic forms of precipitation, consisting of microscopic crystals of various rock-forming minerals mixed with more familiar water droplets. The scientific mystery that emerges from this final bombardment period involves the apparent impossibility of maintaining stable surface water bodies and organized atmospheric circulation patterns, despite the continued occurrence of impacts large enough to disrupt global environmental conditions. Yet geological evidence indicates that some surface water bodies persisted through multiple major impact events, suggesting the operation of rapid recovery mechanisms that can restore stable surface conditions within centuries or millennia, rather than the millions of years that might be expected from the magnitude of the disruptions. This resilience implies the development of feedback systems between atmospheric, hydrological, and geological processes that actively stabilize planetary environmental conditions against external perturbations. Current theoretical models propose that the key lies in the emergence of buffering mechanisms where large atmospheric water vapor inventories and substantial surface water reservoirs create inertia against rapid environmental change, enabling the planetary system to absorb the energy from major impacts without undergoing complete transitions back to the extreme conditions that characterized earlier periods. The mathematical analysis of these feedback systems requires sophisticated modeling of coupled atmospheric hydrological geological processes operating under conditions that have no modern analogues, making precise predictions difficult and leaving many aspects of late Hadean environmental stability as active areas of scientific research. The magnetic field achieves full operational status as the circulation patterns in the liquid outer core stabilize around the configuration that will persist throughout the remaining history of the planet, creating magnetic protection equivalent to the modern Earth's magnetic field and establishing complete shielding against solar wind erosion of atmospheric and surface materials. This magnetic maturation enables the final transition from a planetary environment dominated by atmospheric escape and surface instability to one where atmospheric and hydrological inventories can accumulate and persist over geological timescales. The stable magnetic field also provides protection against the increased radiation levels associated with the final major impacts, preventing the atmospheric disruption that would otherwise result from the electromagnetic pulses and charged particle emissions generated by impact-related shock heating of crustal materials. The crustal evolution completes its primary phase as the global coverage of solid rock achieves sufficient thickness and mechanical integrity to support the development of recognizable geological structures and resist major deformation by the convective processes operating in the underlying mantle. The crustal composition begins to show the first signs of differentiation beyond the simple, mafic assemblages that dominated earlier crustal formation. As ongoing volcanic processes and chemical weathering start to create more evolved rock types that will eventually lead to the formation of continental crust with compositions distinct from the oceanic crust that characterizes most of the early crustal formation. The mechanical properties of the maturing crust enable the preservation of impact structures and other geological features for extended periods, creating the first substantial geological record that will eventually allow reconstruction of early Earth history. The atmospheric composition achieves its Hadean equilibrium configuration, dominated by water vapor and carbon dioxide at pressures approximately 8 to 10 times higher than modern atmospheric pressure, with trace amounts of nitrogen, noble gases, and sulfur compounds that reflect the balance between volcanic outgassing and atmospheric escape processes operating under the protection of a mature magnetic field. This atmospheric composition will persist with only gradual modifications for hundreds of millions of years, providing stable environmental conditions that will eventually enable the development of the complex atmospheric chemistry necessary for life. The atmospheric circulation patterns mature into organized global systems that transport heat, moisture, and chemical species between different climatic zones, establishing the meteorological processes that will eventually evolve into the complex weather systems that characterize modern planetary climates. The hydrological cycle reaches its first mature configuration as surface water bodies achieve sufficient size and stability to participate in organized oceanic circulation patterns, creating the first ocean-like water bodies in Earth's history, though still much smaller and more ephemeral than the vast oceans that will eventually cover most of the planetary surface. These early oceanic systems begin to participate in global heat transport processes, moving thermal energy between different latitudes and creating the first oceanic climate regulation mechanisms. The water chemistry of these early oceans remains exotic compared to modern seawater, heavily loaded with dissolved volcanic gases and metallic ions, but begins to show the first signs of chemical buffering that will eventually stabilize oceanic composition against rapid changes. The thermal evolution of the planet stabilizes around the configuration that will characterize the mature Earth system, with internal heat production from radioactive decay balanced by heat loss through surface radiation and convective transport processes, creating stable thermal gradients that will drive mantle convection and plate tectonic processes throughout the remaining history of the planet. The surface temperatures stabilize in the range where liquid water can exist permanently over most of the planetary surface, though still much warmer than the moderate temperatures that will eventually characterize Earth's climate during periods of biological flourishing. The geothermal heat flow approaches values that will maintain geological activity without the extreme volcanism and crustal instability that characterized earlier periods. The chemical evolution of surface materials accelerates as liquid water becomes permanently available to participate in rock-water interactions, creating the first substantial chemical weathering and erosion processes that will eventually sculpt complex landscapes and transport dissolved materials from continents to oceans. These weathering processes begin to consume atmospheric carbon dioxide through carbonate formation reactions, establishing the first significant carbon cycle processes that will eventually help regulate planetary climate over geological timescales. The chemical differentiation of surface materials also begins the formation of sedimentary rocks, as weathering products accumulate in topographical depressions and undergo diagenetic alteration. The biological potential of the planet approaches its first realization as surface conditions stabilize within ranges that could theoretically support primitive life forms, though the actual emergence of life remains hundreds of millions of years in the future and will require additional atmospheric and chemical evolution to create the specific conditions necessary for biological processes. The establishment of permanent surface water bodies, stable atmospheric composition, and active geochemical cycles creates the environmental framework within which life will eventually emerge. Though the chemical composition of the early oceans and atmosphere remains far from optimal for biological processes, the time scales that govern this final Hadean transition reflect the achievement of stable interactions between all major planetary systems, creating temporal relationships that will persist throughout the remaining history of Earth's evolution, from rapid hydrological and atmospheric processes operating over periods of days to years, to intermediate geological processes operating over thousands to millions of years, to long-term planetary evolution processes operating over hundreds of millions to billions of years. The violence fades like a fever breaking, like the last echoes of thunder rolling away across a landscape that finally knows silence. The Great Bombardment concludes not with a final catastrophic impact, but with the simple absence of new collisions. As the proto-Earth's gravitational dominance sweeps the last debris from its orbital neighborhood, and space around the planet settles into the vast emptiness that will characterize the remainder of solar system history. The surface temperature continues its patient decline toward values that will eventually welcome the chemistry of life, though that welcome remains hundreds of millions of years distant. Separated from this moment by an interval of cooling and chemical evolution that stretches beyond easy comprehension, the atmosphere breathes with the rhythm of a world finally learning to rest. Water vapor rising from the warming lakes and condensing into clouds that drift across landscapes unmarked by any footprint, any consciousness, any purpose, beyond the patient working of physics and chemistry, toward configurations of increasing complexity. The magnetic field settles into its protective embrace around the planet, shielding the precious atmosphere and surface water from the eternal wind that flows outward from the sun, creating the first stable sanctuary in Earth's orbital zone, where delicate processes can unfold without constant disruption. The first stable day-night cycles begin to establish their rhythm across a world that has known only chaos since its formation, as the planet's rotation settles into patterns that will persist for geological ages, marking time with the slow precision of celestial mechanics rather than the random violence of impact dynamics. The young moon, born from the same catastrophic collision that nearly destroyed the proto-Earth, begins its gravitational dance with its parent world, pulling the first true tides across shorelines that will exist long enough to be shaped by the gentle persistence of moving water rather than the instant devastation of cosmic impact. The last magma cools in the final volcanic vents, marking the end of the global magma ocean that has defined Earth's interior since the earliest stages of accretion, leaving behind a differentiated planet with the core mantle crust structure that will power plate tectonics and maintain geological activity for billions of years. The heat generated by radioactive decay settles into patterns that will drive convection in the mantle and create the thermal engine that will eventually sculpt continents and ocean basins through the patient working of geological time. The chemical cycles that will eventually regulate planetary climate begin their first tentative operations as carbon dioxide dissolves in the cooling surface waters and reacts with freshly formed crustal rocks. establishing the feedback mechanisms that will maintain habitable conditions throughout the tumultuous climate changes that await in the planet's future. The first rain falls on landscapes that will remember its touch long enough for streams to carve valleys and chemical weathering to create soils, beginning the slow transformation of barren rock into the complex surface materials that will eventually support the chemistry of life. The silence that settles over this cooling world carries within it the potential for 4 billion years of geological evolution, biological innovation, and the eventual emergence of consciousness capable of looking back across this vast temporal gulf and understanding the violence that was necessary to create the peace. The Hadean Eon draws to its close not with drama, but with the simple achievement of stability. As Earth transitions from a world defined by catastrophe to one where gradual change will shape the landscapes and atmospheres that will witness the emergence of life, the evolution of complexity, and the eventual development of intelligence capable of comprehending its own cosmic origins. In this moment of transition, the planet rests between its violent past and its living future, a cooling sphere of rock and water and atmosphere that has learned the secret of persistence, that has discovered how to maintain the delicate balance of conditions necessary for the chemistry of complexity to begin its patient work toward consciousness and understanding, and the capacity for wonder at the vast scales of time that separate any moment of awareness from the cosmic violence that made that awareness possible. The Hadean ends as it began, in silence, but now it is the silence of completion rather than the silence of emptiness, the quiet of a world that has become ready for the next chapter in its evolution, the patient interval during which chemistry will learn to become biology, and simplicity will discover the pathways toward complexity and awareness. Sleep well, young Earth. The universe is vast, and time is patient, and the story that begins with your cooling will span eons beyond imagining before consciousness emerges to tell it.